Let me first of all write the definition of electrolysis. Then exactly I'll make you understand what this electrolysis is all about. Okay. Electrolysis. Electrolysis, my dear students, it is the process. It is basically the process of decomposition of an electrolyte, into its elements by the supply of direct current. What it means, you'll get the idea in some time. First, take a note of this statement. Number one. Number two, the device in which electrolysis is carried out that device is called as electrolytic cell. That device is called as electrolytic cell. Point number two, take a note of this. Point number three. If you remember, in case of galvanic cells, the cell reactions used to be spontaneous, right? They used to be spontaneous. In case of your Daniel cell, galvanic cell, etc. Right? In case of electrolysis, I'll say reactions are made spontaneous. By the help of direct current. Reactions are made spontaneous by the help of direct current, which are otherwise non-spontaneous. Non-spontaneous. Okay. One more point I'm mentioning here. In the electrolytic cell, we'll be using two electrodes. One is your anode, one is your cathode. And do remember, in case of electrolytic cell, the anode carries the positive charge and the cathode carries the negative charge. Whereas in case of your galvanic cell, if you remember, in case of galvanic cell, the rod of anode used to carry the negative charge and the rod of cathode used to carry the positive charge. Here it's reverse. Anodic rod here carries the positive charge, cathodic rod here carries the negative charge, right? And all the other things are same. At anode, oxidation takes place, which involves loss of electrons, and at cathode, reduction takes place, which involves the gain of electrons. Now let's try to understand all these things in detail. I believe you have taken a note of all these things. Okay, so let's try to understand all these things in detail now. My dear students, in order to make you understand the electrolysis, I'll be taking one example, with the help of which you'll particularly understand what this electrolysis is all about. Okay, what this electrolysis is all about. So I'm going to do the electrolysis of molten NaCl, and automatically you'll get the idea what this electrolysis exactly is. Okay, so first of all, I will be taking a container over here. So imagine this is the container, right? My dear students, in this particular container, let's say I am keeping molten NaCl. In this particular container, I am keeping molten NaCl. Now, first of all, you must be thinking what this molten NaCl is all about. Imagine that you have taken NaCl solid in the container, and you have heated it up, and you have heated NaCl solid till the extent it gets converted into liquid, right? So imagine you have taken solid NaCl in the container and you have started heating it up. There will be a time when this NaCl solid will get converted into NaCl liquid, and that NaCl liquid is something which I call as molten NaCl. So I have got molten NaCl in this particular container. Okay. Now, my dear students, one thing. If there is molten NaCl in the container, can you let me know how many types of ions will be there in the container? There will be two types of ions. One is going to be your Na positive and one is going to be your Cl negative. Correct? Now, dear students, what exactly we shall be doing? I'll be inserting two rods here in this solution. These are the two rods which are inserted in this particular solution. And these two rods I'm connecting with the battery. These two rods I'm connecting with the battery over here. Okay. That rod which is connected with the negative terminal of the battery will carry the negative charge, and that rod which is connected with the positive terminal of the battery will carry the positive charge. And as I told you, the negatively charged rod here is what I call as cathode, and the positively charged rod here I'll be calling as anode, right? And you know, at cathode what happens? At cathode reduction takes place, and reduction is nothing, it is just the gain of electrons. And similarly, at anode I must say oxidation takes place, right? And oxidation involves loss of electrons. Okay. Now, my dear students, let's exactly get to know what, when you connect these rods with the external battery, let's get to know what happens at anode and cathode. Let's get to know what happens at anode and cathode. So first of all, let's try to analyze the things which are going to happen at cathode. Cathode is your negatively charged rod. Can I say this negatively charged rod is going to attract the positively charged ions from the solution? Absolutely, this negatively charged rod is going to attract the positively charged ions from the solution towards itself. So this Na positive is attracted by this particular rod, and similarly, Cl negative is attracted by this particular positively charged rod. Perfect. So can I say this Na positive is going towards cathode? This Na positive is going towards cathode, and at cathode what happens? Reduction happens. So the Na positive which is going towards cathode, I must say this Na positive at cathode will undergo reduction. Reduction involves gain of electrons. So I must say at cathode, your Na positive, it will undergo reduction. It will gain one electron and will get converted into Na solid, right? And this particular Na solid, it will start getting deposited on this particular rod. It will start depositing on this particular rod. The first question which is asked, the products of electrolysis. What is happening at cathode when you do the electrolysis of molten NaCl? You'll directly say at cathode, it is the sodium metal which is being deposited. It is the sodium metal which is being deposited. In the similar way, if I ask you what is happening at anode oxidation takes place, right? At anode, Cl negative will go and will undergo oxidation, right? Cl negative at anode will undergo oxidation. Oxidation involves loss of electrons. So the reaction has to be 2 times Cl negative, right? It will get converted into Cl2 gas, and with this, you will be getting 2 electrons as well. Perfect. So my dear students, the question that's asked here, what is happening at cathode? What are the products of electrolysis? You'll directly remember at cathode, it is basically the sodium metal which is being deposited. Sodium metal is being deposited. And if I ask you what is happening at anode, it is the gas which is getting liberated. So at anode, Cl2 gas is getting liberated, right? At anode, it is the Cl2 gas which is being liberated. Okay. This is the first point which you need to remember in case of this particular electrolysis, right? I hope you got the idea of how this electrolysis exactly happens. Now, my dear students, tell me one thing. The device in which electrolysis takes place. What do you call this device as? You call this as electrolytic cell, right? My dear students, can I say in this electrolytic cell, an external voltage, an external supply is used, an external source is used, which is sending the current in the solution, then only these reactions are happening. Absolutely. Right? You have used an external battery here. You have used the battery here. Right? So what this battery exactly does, it is sending the current in the solution due to which these reactions are happening over here. Right? So with the help of current, the reactions are happening. So the reactions which were supposed to be non-spontaneous, we are making them spontaneous with the help of this external current, with the help of this particular current. Okay? So can I say the non-spontaneous reactions are made spontaneous, right? We are making sure the reactions which were otherwise being non-spontaneous, we are making those non-spontaneous reactions to happen with the help of the current. Okay, with the help of the current. Perfect. This particular cell in which the cell reactions are happening with the help of the current which goes into the solution. This overall process is something which you call as electrolysis. I believe it's clear to everyone. Yeah? Is it clear to everyone? Let me know once in the chats quickly. Let me make you understand one more. Look at this particular scenario. Let's do the electrolysis of molten PbBr2. You'll understand it in a better way. See, first of all, this is the container which I have. And in this particular container, what have I kept? I have kept PbBr2, which is molten PbBr2. So basically in the container, what kind of ions do we get? We'll be having Pb di positive ions and Br negative ions in this particular container, right? So insert two rods here. You have inserted two rods here. Now connect these rods with the battery, right? This is negative, for example. This is positive. Negative over here is called as cathode. This positive over here is called as anode, right? Now, can you let me know what's going to happen? At cathode, reduction takes place. Reduction means gain of electrons. So this particular cathode, this negatively charged rod, is going to attract Pb di positive towards itself. And this positively charged rod is going to attract Br negative towards itself, right? So I would say at cathode, Pb di positive will undergo reduction. At cathode, reduction takes place. And at cathode, Pb di positive is going. So Pb di positive will go to the cathode and undergo reduction, right? So what has to be the reaction? The reaction has to be Pb di positive will undergo reduction, will gain 2 electrons and will get converted into Pb solid, right? Similarly, what is happening at anode? I'll say at anode, Br negative will go and will undergo oxidation. Oxidation means loss of electrons. So the reaction has to be 2 times Br negative will give Br2, and with that you'll be writing 2 electrons. So just tell me in the nutshell what is happening at cathode and anode. So you'll directly say at cathode, lead is being deposited. At cathode, lead is being deposited. And at anode, it is Br2 which is being liberated. Right? Simple. Simple, guys. So right now I'm doing the electrolysis of molten electrolytes. Perfect. I believe you can do the electrolysis of anything. Any molten electrolyte you can do. Now, my dear students, there comes a point. Since I've told you how to do the electrolysis of what? How to do the electrolysis of molten electrolytes. Now, you can keep the electrolyte in aqueous form as well. What about aqueous NaCl? What about the electrolysis of aqueous CuSO4? Right? What about the electrolysis of aqueous PbBr2? What about them? There are few things which you need to know before going into the details of the electrolysis of aqueous electrolytes. Right? Okay, let's try to understand. In simple way. First of all, I want you guys to remember 2 reactions. One reaction is something which I'll be calling as oxidation reaction of water. Another reaction I'll be calling as the reduction reaction of water. These are 2 reactions which I would want you guys to remember first of all. One is oxidation reaction of water, one is reduction reaction of water. Okay, have a look. Have a look, my dear students. Have a look, understand. If I ask you, what is the oxidation state of this oxygen here? It is -2. What is the oxidation state of oxygen here? It is 0. So minus 2 to 0 means increase in the oxidation state. Increase in the oxidation state is something which we call as oxidation. Oxidation involves loss of electrons. So in this particular process, when water will be getting converted into O2, what will happen? Loss of electrons will happen, right? Loss of electrons will happen. And this particular reaction, you are going to remember directly from now onwards. That too in the balanced format. This reaction is called as oxidation reaction of water. In the similar way, in the reduction reaction of water, what is going to happen? Electrons are not going to be lost. Electrons are going to be gained. Have a look. If you look at this particular hydrogen, its oxidation state is +1. This hydrogen, its oxidation state is 0. +1 to 0, decrease in the oxidation state. +1 to 0, decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. And reduction means gain of electrons. Have a look, electrons are being gained here. Electrons are being gained here. This particular reaction I'm calling as the reduction reaction of water. So first, take a note of these two reactions. They are important. Why they are important? You will get the idea in some time. First one is called as oxidation reaction of water, in which loss of electrons is happening. Second one is called as the reduction reaction of water, in which gain of electrons is happening. Right? In which gain of electrons is happening. Perfect? Right, guys? Now, there is a term that's called as discharge potential. How do you define the discharge potential? How do you exactly define the discharge potential? It is defined as the potential at which an ion is discharged at the electrode. The potential at which an ion is discharged at the electrode. Let me make it simple for you. Let me make it simple for you, right? If I make it simple for you, just a second. Let me make it simple for you. Let me write it like this. The work to be done by the electrode. The work to be done by the electrode in order to attract the oppositely charged ion, in order to attract the oppositely charged ion towards itself. See, discharge potential actual definition is this. The potential at which the ion is discharged at the electrode, right? But just to make you understand in simplified manner, I've mentioned it like this. Now, what it means exactly, let's get to know that. See, guys. For example, I have to do the electrolysis. Let's say I have to do the electrolysis of aqueous NaCl. Imagine that I have to do the electrolysis of aqueous NaCl, right? My dear students, this is the container which we have. And in this particular container, what I'm keeping aqueous NaCl. If I'm keeping aqueous NaCl, that means there is NaCl as well as water, right? So how many types of ions will be there? There'll be Na positive, there'll be Cl negative. Since there is water also in the container, so there'll be H positive ions, there'll be OH negative ions. As simple as that, right? Now, my dear students, imagine you have introduced two rods here. These are the two rods which you have introduced, correct? Now you're connecting them with the external battery. This rod gets negative, this rod gets positive. Negative one, that's your cathode. Positive one, that's your anode. Okay, that's your anode. Perfect. Now guys, try to understand. This cathode, this negatively charged rod, this cathode, it carries a negative charge, right? Now this negatively charged rod, it will try to attract the positively charged ion towards itself. So it will try to attract this one as well as this one towards itself. Perfect. Similarly, the positively charged rod will try to attract this one as well as this one towards itself, right? This is clear. Now tell me one thing. Since this negatively charged rod is attracting Na positive as well as H positive towards itself. So basically, both Na positive as well as H positive, they would want to undergo reduction here at cathode. Similarly, Cl negative as well as OH negative, both the anions would want to go to anode and both the anions would want to get oxidized at anode, right? Perfect. See, we have got two cations here. Perfect. So both these cations, they would want to go to the cathode and they would want to undergo reduction. Similarly, both these anions would want to go to anode and they would want to undergo oxidation. But among these two ions, which one will actually undergo reduction? Among these two ions, which one will undergo oxidation? That depends on the discharge potential of these ions. That depends on the discharge potential of these ions, right? Let me tell you that cation among the two, which has got lower discharge potential, will undergo reduction among the two. That anion among the two which has got lower discharge potential will undergo oxidation at anode. In simpler words, if you guys want to understand this in simpler words, I wrote a statement here. The work to be done by the electrode in order to attract the oppositely charged ion towards itself. Have a look. This electrode, it is going to attract Na positive as well as H positive, right? So when this electrode will be attracting this Na positive towards itself, that means the electrode is performing some work here. It's attracting the Na positive towards itself. The electrode is attracting H positive towards itself. It is performing some work, right? So wherever the amount of work to be done by the electrode is less, I'll say that particular ion will have the lesser discharge potential, right? So among these two ions, again I'm telling you, among these two cations, that cation which has got lower discharge potential, that cation wherein electrode has to perform lesser amount of work to attract it, that cation will undergo reduction. Okay. Similarly, look at these two. These are anions basically. They would want to go to anode, they would want to undergo oxidation. But I'm telling you that anion whose discharge potential is less will undergo oxidation. So I would say among these two anions, that anion for which electrode has to do lesser amount of work to attract it towards itself, that anion will undergo oxidation. I hope this is clear. Now, how come you can tell whether among these two, which one has got lesser discharge potential? Among these two, which one has got lesser discharge potential? For that purpose, I want you guys to remember one series over here. This is something which I want you guys to remember. One is the discharge potential series of cations and one is the discharge potential series of anions. Imagine in the container, there is H positive and there is Na positive. Okay. Now, which one has got lesser discharge potential? H positive has got lesser discharge potential than that of Na positive. So if I ask you which ion among the two will undergo reduction at cathode, you'll directly say it is H positive which will undergo reduction at cathode, right? Because the discharge potential is less, right? Actually, how do we define discharge potential? The potential at which the ion is discharged at the electrode. That potential at which ion is discharged at the electrode. Perfect. And this ion gets discharged at lower potential basically. That's why it will undergo reduction at cathode. Similarly, if you look at the anions, in the case which I gave you a few minutes back, aqueous NaCl, right? There are Cl negative ions and OH negative ions. There were Cl negative ions and OH negative ions. Now, among these two ions, which one has got lesser discharge potential? It's Cl negative, right? Among Cl negative and OH negative, which one has got lower discharge potential? It is Cl negative. So Cl negative will undergo oxidation at anode. Cl negative will undergo oxidation at anode. As simple as that. Correct? Perfect. Cl negative, its discharge potential is less. It gets discharged at lower potential basically. Okay? Or I can tell it in simpler ways. In order to attract Cl negative towards itself, anode has to do lesser amount of work. Right? I hope this is clear. Now try to understand all these things in detail now. See guys. For example, the first topic which I'm mentioning here, what is that? Just a second. For example, I'm writing the heading as electrolysis of. Try to understand this. Electrolysis of aqueous NaCl. And my dear students, the electrodes which I'm using, they are inert electrodes which I'm using. Okay, now tell me one thing. Now tell me one thing. Let's say this is your electrolytic cell. In this electrolytic cell, you have got aqueous NaCl. That means there will be Na positive, there will be H positive, there will be Cl negative, there will be OH negative in this container. So two types of cations, two types of anions. This is a rod. This is one more rod connected with the external battery, right? This is negative. This is positive. Negative is your cathode. Positive is your anode. Perfect. Now, this negatively charged rod, it will try to attract Na positive as well as H positive towards itself. So both these ions would undergo, both these ions, they would want to undergo reduction at cathode. But that cation will undergo reduction whose discharge potential is less. Now compare Na positive and H positive. Na positive and H positive. Which one has got lesser discharge potential? Na positive and H positive. Which one has got lesser discharge potential? Na positive and H positive. Which one has got lesser discharge potential? It is H positive which has got lesser discharge potential. My dear students, if H positive has got lower discharge potential, can I say it is going to be H positive which will undergo reduction here? Absolutely. Right? Absolutely. Now among Cl negative and OH negative, which one will undergo oxidation at anode? Cl negative, its discharge potential is less, so it will undergo oxidation at anode. Right? So if I ask you what will be the reaction at anode now? At anode, Cl negative is undergoing oxidation. It will lose electrons. So the reaction has to be 2 times Cl negative. It gives Cl2 plus 2 electrons. Right? Now if I ask you what will be the reaction at cathode? What will be the reaction at cathode? At cathode, reduction will take place. Reduction of what? A reduction of H positive. This H positive has come from where? This H positive has come from where? H positive has basically come from water. So I would write the reduction reaction of water here. I would write the reduction reaction of water here. Right, my dear students? And I hope you remember what about the reduction reaction of water? Few minutes back only I told you. What about the reduction reaction of water? Look at this particular slide. This is the reaction. This is the reaction which is what you call as the reduction reaction of water. And this is going to happen. This is going to happen at cathode. This is going to happen at cathode. Right? This is going to happen at cathode. Let me know once in the chat if it is clear. So this is going to happen at the cathode. Perfect. So at cathode, it's 2 times water plus 2 electrons. It gives H2 plus 4 times OH negative. This is the reaction which is taking place at cathode. So in short, tell me one thing. When we do the electrolysis of aqueous NaCl, at cathode, what is happening? At cathode, it's H2 gas which is being liberated. It is H2 gas which is being liberated. And at anode, what is happening? At anode, something was being deposited, I guess, or gas was liberated. Gas was liberated. Which one? At anode, Cl2 gas was liberated. So at anode, you got to know Cl2 gas is liberated. At cathode, you got to know H2 gas is liberated. Right? I hope this is clear to everyone. Clear, guys? Let me know once in the chats. Let me know once in the chats quickly. Right? So the reaction has to be 2 times water plus 2 electrons. 2 times water plus 2 electrons gives H2 plus 2 times OH negative. This is the reduction reaction which is happening at the cathode, and it's your H2 gas which is being liberated at the cathode. So these are the two things which I want you guys to remember. For example, you are doing the electrolysis of aqueous CuSO4. Let's imagine that you are doing the electrolysis of aqueous CuSO4. Imagine this rod carries the negative charge. Imagine this rod carries the positive charge, right? And in the solution, how many types of ions will be there? In the solution, how many types of ions will be there? Tell me that. In the solution, how many types of ions are there? You are doing the electrolysis of aqueous CuSO4. So there are Cu di positive ions, there are SO4 di negative ions, there are H positive ions, and there are OH negative ions. Correct? So this particular cathode, and this is your anode, right? At cathode, reduction will happen. Now this negatively charged rod will attract Cu di positive as well as H positive towards itself. But among these two, which one will undergo reduction here? The one which has got lesser discharge potential. The one which has got lesser discharge potential. Now tell me, among Cu di positive and H positive, which one has got lesser discharge potential? It is Cu di positive. So Cu di positive is undergoing reduction at cathode. So the reaction has to be Cu di positive plus 2 electrons gives what? It gives copper solid. So basically here, it is copper solid which is being deposited. It is copper solid which is being deposited. Similarly, you have got two types of anions, OH negative, SO4 negative. Now both would want to go to the anode and both would want to undergo oxidation. But among these two, which one will undergo oxidation? The one which has lesser discharge potential, that's OH negative. OH negative has got lesser discharge potential, so it will undergo oxidation at anode. But if I ask you from where this OH negative has come, you will say this OH negative has come from water. This OH negative has come from water, right? So OH negative has to go to the anode and will undergo oxidation, but this OH negative has come from the water. So you'll write the oxidation reaction of water. This was your oxidation reaction of water. And due to the oxidation of water, what is happening? O2 gas is liberated. O2 gas is liberated. And at cathode, copper solid is deposited. So these are the products of electrolysis which you have to remember. Is it done? Is it done, guys? Is it clear? Let me know once in the chats quickly. Let me know once in the chats quickly. Yeah? Say yes or no in the chats quickly. I believe you got the concept, right? The electrodes which I used during the electrolysis, those were your inert electrodes, right? Those were your inert electrodes like platinum. The actual topic, my dear students, which we have to discuss, what is that? The actual topic which we are going to discuss, that is Faraday's laws, from which questions frequently come in your examination, right? Faraday's, it has given two laws here in electrolysis, so we are going to discuss these electrolysis, these Faraday's two laws in detail, right? So tell me once in the chats whether you can do the electrolysis of all the electrolytes with the help of discharge potential series. Right? Whatever electrolyte I give you, with the help of discharge potential series of cations and anions, can you do the electrolysis of every electrolyte? Right? Will you be able to guess what is happening at cathode and what is happening at anode? Just tell me that. Just tell me that. Perfect. Then let me move on to Faraday's first law of electrolysis. Have a look, people. So till now we got to know at the electrodes either metal is being deposited or gas is being liberated, right? On the electrodes we saw either metal getting deposited or gas being liberated. Now what Faraday's first law suggests that? Faraday's first law tells you that, say, on passing current in an electrolytic solution, the amount of substance deposited or liberated at the electrode, that is directly proportional to the charge which goes into the solution. Basically, you connected the electrodes with the battery. What battery does? It is sending charge into the solution. More the charge that goes into the solution, more will be the amount of substance getting deposited or liberated at the electrode. So mathematically, I can say it like this. The mass of substance in grams, the mass of substance deposited or liberated. This W represents the mass of substance which is being deposited or liberated. That is directly proportional to the charge which goes into the solution. Now, my dear students, if you remove the proportionality sign here, you'll get a constant, which I represent with Z. So it's Z multiplied by Q. What this Z exactly is? This Z is called as electrochemical equivalent. Right? And it is equal to E divided by 96500. What is this E? E is the equivalent weight of same substance which is being deposited or liberated. E is the equivalent weight of same substance which is being deposited or liberated. So I'll say, as per Faraday's first law, mass of the substance deposited or liberated is equal to, instead of Z, you're going to write E. Divide by what? Divide by 96500. Multiplied by what? Multiplied by Q. And Q is the charge. And charge is nothing. That is current multiplied by time. So this is the first result which I would want you guys to remember from now on. With the help of this particular result, we can easily calculate the mass of substance which is being deposited at electrode. Or we can easily calculate the mass of the gas, which is being liberated at the electrode. Perfect, which is being liberated at the electrode. This is the result number 1. Now result number 2. Have a look. Can I write it like this? Mass of the substance deposited or liberated in grams is equal. What is E? E is the equivalent mass of the same substance which is being deposited or liberated. And equivalent mass of the substance which is being deposited or liberated is equal to molar mass of the same substance which is being deposited or liberated divided by n factor of same substance. Right? And in the denominator, what do we have? 96500. In the numerator, we have got I multiplied by T. If you take this molar mass here in the denominator, so what do we get? W divided by M. Mass of substance deposited or liberated divided by molar mass of the same substance. Given mass by molar mass, that's called as moles. So N represents the number of moles of the substance which are being deposited or liberated. N represents number of moles of substance which are being deposited or liberated. It's equal to I multiplied by T divided by N factor of same substance which is being deposited or liberated multiplied by 96500. This is something which I want you guys to remember again. Right? This is something which I want you guys to remember again. Perfect. After this, my dear students, one more thing. For example, this was your question number 1. This was your question number 2. For example, if they ask you to calculate the volume of the gas liberated at STP. If they ask you how much volume of the gas is liberated at the electrode at STP. So for that purpose, to calculate the volume of the gas liberated at STP, first of all, you will be calculating the moles of the gas liberated. And once you calculate the moles of the gas liberated, after that, you will say volume of the gas liberated will be equal to moles of the gas liberated multiplied by what? Multiplied by 22.4 liters. Right? If they ask you to calculate the volume of the gas liberated at STP, this is how you do it. First, you will calculate the moles of the gas liberated multiplied by 22.4 liters. If they do not mention STP, then in the question, they'll give the pressure, they'll give the temperature. Then you'll be using the ideal gas equation and calculate the volume of the gas liberated. Right? I'll try to do certain questions with you so that you get familiar with the types of the questions which can be asked from these results. Okay? But before that, there is one more thing which I would want to discuss with you. One more simple thing which I would want to discuss with you. My dear students, in this particular reaction, if I ask you how many moles of electrons are exchanged, in this particular reaction, as you can see, 12 moles of electrons are exchanged, right? If I ask you if this is a balanced chemical equation, first of all, if this is a balanced chemical equation and I'm asking you to calculate the n factor of A. From the balanced chemical equation, you can easily calculate n factor. How exactly? Let's say n factor of A will be equal to moles of electrons exchanged, that is 12, divided by stoichiometric coefficient of A, that's 1. N factor of A, you'll directly say as 12. For example, if I'm asking about n factor of B, how many moles of electrons exchanged? 12 divided by stoichiometric coefficient 2. So 12 divided by 2 is 6. 12 divided by 2 is 6. So 6 I'll be calling as n factor of B. Similarly, what is the n factor of C? 12 divided by 3, that's 4. 12 divided by 4, 3. 12 divided by 12 divided by 6, that is 2. So these are the respective n factors of these reactants and products. So basically, whenever you'll be given with a balanced chemical equation, from the balanced chemical equation, you can easily talk about the n factors of different substances. What you have to do? Moles of electrons exchanged divided by stoichiometric coefficient of reactant or product, the one whose n factor is to be calculated. Remember this particular thing as well. Now, why am I telling you this thing? See guys, the types of the questions will make you understand why am I exactly telling you all these things. Look at the question carefully. The simplest of all the questions. A solution of aqueous CuSO4. Is electrolyzed for 10 minutes. With a current of 1.5 amperes. So basically, a current of 1.5 amperes is going into the solution for 10 minutes. What will happen? Electrolysis will happen, right? And due to electrolysis, a reaction would have happened at cathode, a reaction would have happened at anode. Perfect. Reaction would have happened at cathode and reaction would have happened at anode as well. Now the question is asking, what is the mass of copper deposited at cathode? They're asking you what is the mass of copper which is deposited at cathode. So first of all, my dear students, you should know when we do the electrolysis of aqueous CuSO4, what is the reaction at cathode. If you remember, a few minutes back only I told you, at cathode, when we do the electrolysis of aqueous CuSO4 at cathode, this is the reaction through which copper is getting deposited. Right? Right, people? Now you will directly use Faraday's first law. We have to calculate the mass of copper deposited, right? Tell me first of all, what is the N factor of copper? What is the N factor of copper here in the reaction? Is equal to moles of electrons exchanged 2 divided by stoichiometric coefficient 1. So N factor of copper is 2 here, right? N factor of copper is 2. Now, I'll be using the equation. Mass of copper deposited in grams is equal to equivalent mass of copper multiplied by I multiplied by T divided by what? 96500. I believe you are done. Equivalent mass of copper is molar mass of copper 63.5 grams divided by N factor of copper. N factor of copper is 2. In the denominator, you have got 96500. What is the value of current? 1.5 amperes of current is passed into the solution for 10 minutes, but use the time in seconds. So multiply it with 60, right? One equation, you're done, right? I think after solving this, you'll be getting the value exactly around 0.3 grams. So what is the 0.3 grams exactly? You can say when we do the electrolysis of aqueous CuSO4, when a current of 1.5 amperes is passed into the solution for 10 minutes, you will say 0.3 grams. 0.3 grams of copper would have got deposited at the cathode, which is something I was supposed to calculate. I believe it's clear. Let me know once in the charts if it is clear. So 0.29 grams is the answer. Yeah? Quickly, guys, quickly. Let me know fast so that we can end the chapter fast. Because we have a lot of things to discuss. So let me know quickly in the chats if it is clear. Yes or no, everyone. Everyone in the chats. Sir, when do you take coordination compounds? When am I going to take coordination compounds? You tell me. Guys, which chapter do you want the next after this electrochemistry? Which chapter do you want the next? Majority wins. Majority wins. Tell me. Which chapter do you want the next? Quickly. After electro, which one do you want to do here? Quickly, quickly, everyone. Just say it, everyone. Nothing is wrong in it. I can see majority is looking for atomic structure. Okay, let me go with atomic structure. Next will be atomic structure, right? All right, look at the next question, guys. Look at the next question. See, or just wait. Let's not do this question first. Let me see. Just a second. Let's do this particular question first. Look at this question carefully. The question is, what is the volume of oxygen? What is the volume of O2 liberated at anode at STP during the electrolysis of aqueous CuSO4? So we are doing the electrolysis of aqueous CuSO4, and you know when we do the electrolysis of aqueous CuSO4, which gas is liberated? It is O2 gas which is liberated. This is something which we know, right? O2 gas is liberated. Now they are asking you to calculate volume of O2 gas liberated at STP. So what do I calculate first? First of all, I'll calculate the moles of O2 liberated. Use the formula. I multiplied by T divided by N factor of what? N factor of O2 which is being liberated. N factor of O2 multiplied by 96500. Right? Now tell me, number of moles of O2 liberated is equal to current, how much? Current of 2 amperes is passed for how many seconds? For 8 minutes. So 8 multiplied by 60, then only it comes in seconds. N factor of O2. N factor of O2 is moles of electrons exchanged. 2 divided by stoichiometric coefficient, that's 1 by 2. The value is 4. So N factor of O2 is 4. Multiplied by what? Multiplied by 96500. So from this particular equation, what do we get? We'll be getting the moles of O2 produced. But am I supposed to calculate moles or volume? I'm supposed to calculate volume. So volume of O2 produced will be equal to moles of O2 produced multiplied by 22.4 liters, right? This is something which you'll be calculating from here. and you'll have to multiply it with 22.4. You'll be getting the volume of O2 produced. Is that clear? Is that clear to you people? If you want to have a look on the exact values, so moles are 0.002 and volume of O2 liberated is 0.05 liter. Yeah? Perfect. I believe this is clear to everyone, right? Let's try to solve a few more questions. Look at this particular question, guys. Look at this particular question. Look at this particular question. As per this particular question is concerned, a current of 96.5 amperes, is passed for 10 seconds through 1 liter of a solution of 0.5 molar aqueous copper sulfate. Calculate the pH of the solution. Calculate the pH of the solution. Try to understand what the question says. As far as this particular question is concerned, we are again doing the electrolysis of aqueous CuSO4, right? That's something which we are doing. We are doing the electrolysis of aqueous CuSO4. And my dear students, we already know that when we do the electrolysis of aqueous CuSO4, we already know the reactions which happen at anode and cathode. This is the reaction at cathode. This is the reaction at anode, right? Now at cathode, what is happening? At cathode, it is just copper is being deposited. Now at anode, what is happening? At anode, water is undergoing oxidation, due to which first O2 gas is produced. At the same time, H positives are also produced, right? H positives are also liberated. At anode, water undergoes oxidation, due to which O2 gas is produced, O2 gas is liberated, and H positives are also generated, and those H positives will enter into the solution. The H positives which we get at anode, these H positives will definitely enter into the solution. Yeah, these H positives will enter into the solution. My dear students, can I say this is the reaction which is going to take care of the pH? This is the reaction which is going to take care of the pH, because through this particular reaction, H positives are generated and those H positives are going into the solution. Right? Perfect. What am I supposed to calculate? I'm supposed to calculate pH. Try to understand one thing. I'm supposed to calculate pH. What is pH basically? P stands for minus log. So minus log of H positive concentration we have to calculate. So can I say in order to calculate pH, we should know what is the total H positive concentration in the solution after the electrolysis is done. Once the electrolysis is complete, after that, you'll find H positives in the solution. Now we will have to calculate the concentration of H positives in the solution after the electrolysis is complete, right? How do I calculate the H positive concentration? Concentration is nothing, it is moles per unit volume. So basically, it is going to be number of moles of H positive divided by volume of solution in liters. So can I say in order to calculate the H positive concentration, I should know the number of moles of H positive which are liberated into the solution. Now how do I calculate number of moles of H positive liberated? With the help of Faraday's first law. I'll say number of moles of H positive liberated is equal to I multiplied by T divided by what? Divided by N factor of H positive. Multiplied by what? Multiplied by 96500. Correct? So number of moles of H positives which are liberated in the solution is equal to, what is current? Current is 96.5 amperes. For how much time? 10 seconds. Divided by, what is the N factor of H positive? N factor of H positive. Moles of electrons exchanged divided by stoichiometric coefficient. 2 by 2 is 1. This is 1. Multiplied by what? 96500. The value comes out to be 10 raised per minus 2. So I'll say these many moles of H positive have gone into the solution. In the solution, you'll find these many moles of H positive. Once you get the moles of H positive, tell me what will be the concentration of H positive in the solution. Moles of H positive in the solution divided by volume of solution in liters. So it is 10 raised per minus 2 divided by, what is the volume of solution? That's 1 liter. So the value comes out to be 10 raised per minus 2 only. So 10 raised per minus 2 molar is the concentration of H positive in the solution. If you got the concentration of H positive in the solution, you can easily calculate pH of the solution. P stands for minus log. It is minus log of H positive. So pH is going to be equal to minus log of 10 raised per minus 2. The value exactly comes out to be 2. So 2 is the pH of the final solution which we get after the electrolysis is done. Let me know once in the chats if it is clear. Quickly guys, quickly in the chats. Quickly in the chats. Similar sort of question. Similar sort of question. Give it a try. Read the question first, then let me know whether you can solve this or not. Read this question first. Read this question quickly. The question is very simple. 1 farad of electricity, 1 farad of electricity, 1 farad of electricity is passed through 10 liter of an aqueous solution of NaCl. So as per the question, you are doing the electrolysis of aqueous NaCl. And since you are doing the electrolysis of aqueous NaCl, what are we supposed to calculate? We are supposed to calculate pH of the solution. My dear students, don't you remember when we do the electrolysis of aqueous NaCl? Don't you remember the reactions at anode and cathode? The reaction at anode, the reaction at cathode. Now, tell me one thing. Which reaction among the two should I consider to calculate the pH of the solution? You tell me. Which reaction among the two should I consider to calculate the pH of the final solution after the electrolysis is done? You tell me. Is it going to be reaction at anode or cathode? My dear students, at anode nothing is happening. Only Cl2 is being liberated. But if you look at cathode OH negatives are also produced. At cathode, OH negatives are also produced. And those OH negatives will enter into the solution. Yeah? Those OH negatives will enter into the solution. Now see, how am I going to tackle this question? First of all, if I ask you, what about the N factor of OH negative? What about the N factor of OH negative? Quickly. It's going to be equal to moles of electrons exchanged divided by stoichiometric coefficient. So 2 divided by 2 is 1. This is the N factor of OH negative. Okay? Now, my dear students, the first thing which I'll be doing, I'll calculate the moles of OH negative. Moles of OH negative which are being produced, which are being liberated into the solution. Moles of OH negative, as per the formula, I multiplied by T divided by N factor of OH negative multiplied by 96500. But do you see, current is not given, time is not given. Current is not given, time is not given. Okay. But I multiplied by T is what we call as Q. Instead of I into T, instead of I multiplied by T, I can declare Q. So I'll say N factor of OH negative, my dear students, will be equal to, what is Q? Q is 1 farad. 1 farad means 96500 coulombs. 1 farad is 96500 coulombs. Divide by N factor of OH negative, that's 1. Divide by 96500. The value is coming out to be 1. So you got to know 1 mole of OH negative is liberated into the solution. Right? During this electrolysis, once this electrolysis is done, you'll find 1 mole of OH negative in the resulting solution. If you got the moles of OH negative, can't we get the OH negative concentration in the container? It has to be equal to moles of OH negative in the container divided by volume of solution in liters. Now tell me, how many moles of OH negative do we have? 1. Volume of solution in liters, that's 10 liter. The value is 10 raised power minus 1 molar. 10 raised power minus 1 molar. So this is the concentration of OH negative in the final solution once the electrolysis is complete. Okay. If you got the OH negative concentration, we calculate POH. P stands for minus log. It's minus log of OH negative concentration. So it is minus log of 10 raised power minus 1. The value comes out to be 1. So you got the POH. If you got the POH, you know at 25 degrees centigrade, pH plus POH is always equal to 14 at 25. So pH from here will be equal to 14 minus 1, which comes out to be 13. Is this clear? Is this clear, people? Is this clear? Let me know in the chats quickly. Done? Look at this particular question. Look at this particular question. Calculate how much current is required. Calculate how much current is required to produce H2 gas at the rate of 1 ml per second under STP. Read the question carefully. Calculate how much current is required to produce H2 gas at the rate of 1 ml per second at STP. So as per the question, we are doing some electrolysis, right? We are doing some electrolysis, due to which what is happening? What is happening? H2 gas is getting produced. Now, as per the question, we have to do electrolysis in such a way that 1 ml of H2 gas should get produced. So how much ml of H2 gas should get produced? 1 ml of H2 gas should be liberated in how much time? In 1 second, right? We have to perform electrolysis in such a way that 1 ml of H2 gas should get liberated in 1 second. In order to liberate 1 ml of H2 gas in 1 second, how much current should enter the solution? That's something which you're supposed to calculate. How much current should enter into the solution such that 1 ml of H2 gas is liberated in 1 second at STP? Correct? There are many ways of solving this question, right? The kind of approach which I've been using till now, I'll use the same approach. See guys, since the condition is STP, right? How much volume has to get liberated? 1 ml. If I ask you, how many moles of H2 are supposed to be liberated? How many moles of H2 are supposed to be liberated? It's going to be 1 divided by 22400. So these many moles of H2 should be liberated. In how much time? In 1 second. Now you already know, can't I write like this? Number of moles of H2 liberated has to be equal. It has to be equal. I multiplied by T divided by N factor of H2 multiplied by 96500. Right? Now, my dear students, first of all, you should understand how H2 gas is produced. How H2 gas is produced. How H2 gas is produced. If you remember, H2 gas is only produced when water at cathode undergoes reduction. When water at cathode undergoes reduction. Due to the reduction reaction of water. Due to the reduction reaction of water, H2 is produced. Right? Due to the reduction reaction of water, H2 is produced. Do you remember that? Do you remember that? Due to reduction reaction of water, H2 is produced. So, you can write either the reduction reaction of water or in simpler ways, you can write the reaction in this manner. You can either write reduction reaction of water, right? Or you can write the reaction in this manner. Perfect. The choice is all yours. Answer will be same. Okay. Now, what is the N factor of H2 here? Moles of electrons exchanged divided by stoichiometric coefficient. So 2. So number of moles of H2. Number of moles of H2 liberated. We already know it. That's 1 upon 22400. So number of moles of H2 liberated is 1 upon 22400 is equal. Current, we have to calculate. Time, 1 second. N factor of H2, that is 2. Multiplied by 96500. One equation, one unknown. Can't you get the I value from here? Can't you get the I value from here? And as far as I remember, the value of I will come out to be 8.61 amperes. So what is meant by this 8.61 amperes? Just tell me that. Just tell me that. What is meant by it? It means that 8.61 amperes should pass into the solution. Then only 1 ml of H2 gas will be produced in 1 second at cathode. Yeah? Is it clear? Is it clear, guys? Quickly. Look at this question. Just tell me, can you solve this question on your own? Can you solve this question on your own quickly? Let me know in the chats. Let me know in the chats quickly. Can you solve this question on your own? Till then, let me find one more question. One more different type of question, which can be asked from the same. This is something which you can solve now, right? It is of similar pattern. Similar pattern. It is just volume is given in liters here. So you do not have to divide with 22400. You have to divide with 22.4. I'm giving you this as the homework. You are going to try it and write the answer in the comment section at the end. In the last session, I gave one question. Only 6 people gave the correct answer. Only 6 people gave the answer in the last session. Right? But I want you guys to, everyone to solve this question and write the answer in the comment section. Okay? Now, Let me give you one more question. The question is like this. I'm writing the question. The question is, for example, the density. The density of copper is equal to 8.95 grams per centimeter cube or grams per ml. Find the charge. Find the charge required. Find the charge required to plate an area of 100 centimeter square. Of 100 centimeter square to a thickness of 10 raised power minus 2 centimeters. 10 raised power minus 2 centimeters using copper sulfate solution. Using CuSO4 solution. Look at the question carefully and give it a try. Look at the question carefully and give it a try. First, read the question. First, read the question. First, read the question. Sorry. Okay. Guys, have a look. I'll solve this question. You just have a look on and remember the approach. The question is, the density of copper is 8.95 grams per centimeter cube. Find the charge required to plate an area of 100 centimeters square to a thickness of 10 raised power minus 2 centimeters using copper sulfate solution. My dear students, when we do the electrolysis of aqueous CuSO4, what happens at cathode? At cathode, Cu dye positive gains 2 electrons, gets converted into copper solid. And that copper solid is deposited on the cathode, right? Let's assume that this is your cathode. It's a plate. It is your cathode, for example. This is your cathode. And at cathode, what is happening? Reduction is happening. Reduction of what? Cu dye positive. So Cu dye positive from the solution is gaining 2 electrons, getting converted into copper solid. This is your cathode. This is your cathode on which this copper solid is being deposited. So this is a plate on which copper solid is being deposited. Copper solid is being deposited on this plate, right? As per the question is concerned, the area of cross section of this particular plate, it's 100 centimeters square. Dear students, if the area of cross section of this plate is 100 centimeters square, that means the copper which is being deposited here, that has to cover the area of 100 centimeters square, right? So the copper which is being deposited, it has to cover the area of 100 centimeters square, right? Since we are doing the electrolysis of copper sulfate, what is happening? At cathode, reduction is happening. Copper solid is being deposited. We have to continue the electrolysis. Till number 1, till the entire surface gets covered with the copper. And after that, the thickness of the copper on this plate should be 10 raised power minus 2 centimeters. Till then, we have to continue the electrolysis. I hope you're getting this, right? We have to continue the electrolysis till the entire surface of the plate, till the entire surface of the electrode is covered. And at the same time, first entire surface should get covered. After that, the thickness of the copper on the plate should be 10 raised power minus 2 centimeters. If I ask you, indirectly, how much volume of copper are we depositing on this plate? How much volume of copper are we depositing on the plate? Tell me that. Area of cross section multiplied by thickness. Area of cross section is 100 centimeters square. Thickness is 10 raised power minus 2. So 100 multiplied by 10 raised power minus 2 is going to be 1 cubic centimeter. So this much volume of copper, basically we are depositing on this plate. Right? This much volume of copper we are depositing on the plate. Correct? Now tell me, is the density of copper given to you? Absolutely. How much? 8.95 grams per centimeter cube. Can I say density of copper is nothing? It is mass of copper. deposited divided by volume of copper. Volume of copper in centimeter cube. This is basically 8.95 grams per centimeter cube. Correct? Agreed? What is the volume of copper which is being deposited? 1 centimeter cube. 1 centimeter cube is being deposited. So 1 multiplied by this. So I'll say mass of copper deposited has to be 8.95 grams. So first of all, you got to know the mass of copper which you are depositing. So we have to deposit 8.95 grams of copper, right? We have to deposit 8.95 grams of copper. In order to deposit 8.95 grams of copper, what is the charge? What is the charge which should go into the solution? Calculate the charge that should go into the solution. Okay, calculate the charge that should go into the solution so that 8.95 grams of copper is deposited. So I'll directly say mass of copper deposited as per Faraday's first law has to be equal. Equivalent mass of copper multiplied by I multiplied by T divided by 96500. Correct? So what mass of copper we are going to deposit? 8.95 grams is equal to equivalent mass of copper is molar mass of copper divided by what? Divided by n factor of copper. Calculate the n factor of copper. Electrons exchanged divided by stoichiometric coefficient. So this is 2. In the denominator, it's 96500. Right? I multiplied by 2, I can call directly as charge Q. I multiplied by T is something which you call as Q. Perfect. So from this particular result, can't you get the value of Q? Yeah? Can't you get the value of Q? Can't you get the value of Q? Perfect, guys. Is it clear? Is it clear to everyone? Quickly in the chats. Quickly, everyone. Hi, Wassim sir. How are you? I'm doing good, bro. How are you doing? Glad to know that, Rohit. I think this Believers was my last year student. You the same? Who used to follow me on YouTube on the last platform? Right? There was one regular student whose name was Believers. Maybe you're the same. Anyways, have a look. So from this particular equation, we can easily get the Q value, right? And Q from here, you are going to get in coulombs, right? Perfect. So I believe you can easily solve these sort of questions now, right? I believe you can easily solve these sort of questions. So let's move on to the Faraday's second law of electrolysis. Let's move on to the Faraday's second law of electrolysis. First of all, tell me in the chats, whatever types of questions I showed you in the Faraday's first law, will you be able to solve all the types? Will you be able to solve all the types of questions? Say yes or no in the chats. I believe every single thing is clear, yeah? Perfect. Now, let's have a look on Faraday's second law of electrolysis. What this Faraday's second law of electrolysis states. Let's have a look on the definition first, then I'll make you understand. Okay? If a current is passed in two or more electrolytic solutions containing different electrolytes, the mass of substance deposited or liberated in different cells will be in the ratio of their equivalent masses, or the number of equivalents deposited in all the cells will be the same. Now, what is meant by this whole statement? Let's try to understand. See, guys, as far as this particular question is concerned, imagine that I have got, for example, 3 electrolytic cells like this. Let's say I've got 3 electrolytic cells like this. Assume that in this particular container, there is one electrolyte, for example, AB, just to make you understand. In this particular container, there is one more electrolyte, for example, CD. Let's say in this particular container, there is one more electrolyte, for example, EF. So we have got 3 different electrolytes present in 3 different containers. Okay. Now, what exactly I'm doing? Let's put the rods inside. These are the 2 rods in the solution. 2 rods in this particular solution. 2 rods in this particular solution, right? Let me connect these rods. Let me connect these rods. And at the end, let me connect them with the external battery as well. I've connected them with the battery as well. So first thing, my dear students, that rod which is connected with the negative terminal will carry the negative charge, and that rod which is connected with the positive terminal will carry the positive charge. If this is positive, this has to be negative. If this is negative, this has to be positive. This has to be negative, and this has to be positive, right? Okay. Tell me one thing. We have got more than one electrolytic cells containing different electrolytes in series. This is the series combination. This is first of all the series combination, right? This is the series combination. And you know, in the series combination, current remains the same. You know it. So can I say same amount of current is going into this solution? Same amount of current is going into this solution. Same amount of current is going into this solution. So in all the three cells, what will happen? Electrolysis will happen. Due to electrolysis, something would be happening at electrodes. Either metal will be deposited or gas will be liberated. That's something, right? Let's assume, my dear students, let's assume at this particular electrode, let's assume A is being deposited and B is being liberated. For example, just to make you understand, let's assume at this particular electrode, what is happening exactly? At this particular electrode, just a second, guys, just a second. Let's assume that on this particular electrode, A is being deposited, and here, for example, B is getting liberated. Let's say here, C is getting deposited, and here D is getting liberated. For example, here on this electrode, let's say E is getting deposited, and here F is getting liberated. This is something which I'm assuming. Now, as per Faraday's second law is concerned, whenever you'll be having two or more than two electrolytic cells connected in series, containing different electrolytes, the gram equivalence deposited or liberated at every electrode will be the same. That means I can say the gram equivalence of A deposited at the first electrode will be same as that of gram equivalence of B liberated at the second electrode, which will be same as that of gram equivalence of C deposited, which will be same as that of gram equivalence of D liberated, which will be same as that of gram equivalence of E, similarly, which will be same as that of gram equivalence of F. Perfect. This is something which we call as Faraday's second law. Gram equivalence deposited or liberated at every electrode will be the same only. Perfect. Now, I hope you guys remember how do we calculate gram equivalence. Gram equivalence of the substance is equal to, do you remember? Mass of substance divided by equivalent mass of the substance. Or you can say number of moles of the substance multiplied by n factor of the substance. This was the result to calculate gram equivalence, studied in redox, right? Perfect. Perfect, guys. Now, at the same time, one more thing, then I'll do certain questions so that you can understand it properly. See, guys, for example, I'm taking one electrolytic cell. Which contains an electrolyte. Right? It is connected with the battery, due to which this gets negative, this gets positive. Right? Negative is what you call as cathode here. This is your anode. Let's assume at cathode, some substance A is getting deposited, and let's assume at anode, gas B is getting liberated. Just to make you understand. Now you can use Faraday's second law here as well. You can say gram equivalence of A deposited here should be equal to gram equivalence of B liberated here. You can write it like this. Gram equivalence of A deposited on the first electrode will be always equal to the gram equivalence of B liberated. At the same time, you can do one more thing. You can write the same statement in terms of milli equivalence as well. You can say milli equivalence of A deposited will be equal to milli equivalence of B liberated, right? And my dear students, if you got to know how to write these statements, you are done. You can solve any question of your NEET standard from Faraday's second law. Let me show you one. Look at the question. Let's see what the question is first of all. The question is, during electrolysis of aqueous CaSO4, We are doing the electrolysis of aqueous CO4. The mass of metal deposited is equal to 63.5 grams. Calculate the mass of gas released and volume of the gas released at STP. These are 2-3 questions. Yeah? Try to understand. Try to understand. See guys. As far as the question, we are doing the electrolysis of aqueous CuSO4, right? And when we do the electrolysis of aqueous CuSO4, at cathode copper gets deposited. At cathode copper gets deposited. And at anode, O2 gas gets liberated. This is something which we already know. At cathode copper gets deposited. At anode, O2 gas is released. What Faraday's law says? What Faraday's law says? What Faraday's law says? Can't I say the number of gram equivalents of copper deposited should be equal to the number of gram equivalents of what? The number of gram equivalents of O2 produced. Just equate their gram equivalents, nothing else. Now tell me one thing. Gram equivalents of copper can be written as mass of copper deposited divided by equivalent mass of copper. Similarly, gram equivalents of O2 produced will be equal to mass of O2 produced in grams divided by equivalent mass of O2. Yeah, I think we are done. Aren't we done? Now, my dear students, try to understand. What is the mass of copper which is being deposited? Calculate the mass of gas released. Okay, the mass of copper which is being deposited, that is 63.5 grams. So 63.5 grams of copper is deposited. Divide by equivalent mass of copper. Equivalent mass of copper is molar mass of copper divided by n factor of copper. What is the n factor of copper? 2 divided by 1. That's 2. Is equal to mass of O2 produced. That's something which we have to calculate. Mass of O2 produced divided by equivalent mass of O2 will be equal to molar mass of O2 divided by n factor of O2. N factor of O2 will be equal to electrons exchanged divided by stoichiometric coefficient. So 2 divided by 1 by 2. That comes out to be 4. This term cancel. The value comes out to be 2. Right? 4, 1, 4, 8. So that 8 is here. And this is mass of O2. Perfect. The value comes out to be 16 grams. So you got to know 16 grams of O2 is liberated. You got to know 16 grams of O2 is liberated at anode. 16 grams of O2 is liberated at anode. So we were supposed to calculate the mass of gas released. We got to know 16 grams of O2 is released. And at the same time, we have to calculate volume of gas released too. Right? Yeah? Right? Yash is saying, sir, please show effect of external cell on galvanic cell if possible. I think that is something which I've taught already. Check the first part. Check the first part. That is something which I've discussed with you in the first part. What happens when external battery is connected with the galvanic cell with reverse polarity? I believe I've discussed that. Guys, have I discussed that in the first part? I think yes. Okay, let's solve this question first. Then I'll see whether I have taught that or not. See, so mass of O2 produces 16 grams. What else we have to calculate? Volume. But before volume, let's calculate moles of O2 produced. Moles of O2 produced will be equal to mass of O2 produced divided by molar mass of O2. So these many moles of O2 are produced. So volume of O2 produced has to be moles multiplied by 22.4 liters. The value has to be 11.2. So 11.2 liters of O2 is produced. Perfect. Let me move on. Let me move on to the next question. Look at this particular question. Read the question carefully and let me know whether you can solve this or not. Just read it carefully first. Just read it carefully. 3 electrolytic cells containing zinc sulfate, AgNO3 and copper sulfate respectively are connected in series. A current of 2 amperes was passed until 1.08 grams of silver was deposited at cathode of cell B. How long did the current flow? Okay. What mass of copper and zinc was deposited? Read the question. Tell me, can you solve this question on your own? If you can do, then I'll move on to the next topic. Tell me whether you can solve this question on your own or not. Read it quickly. You solve it. Okay, I'll solve it. See guys, as per the question is concerned, we have taken 3 electrolytic cells. So imagine this is one electrolytic cell, imagine this one more, and imagine this one more. So we have got 3 electrolytic cells. The first one is containing zinc sulfate. The second is containing AgNO3. And the next one is containing what? It's containing CuSO4. All right. Now there are two rods here. Two rods are here as well. And two rods are here as well. Now we will be connecting them with the external battery, right? This is the battery here, negative, this is positive. Perfect. One is negative, one is positive. The negatively charged rod, the negative terminal of the battery is connected here, so it carries a negative, this carries positive, this is negative, this is positive, this is negative, and this is positive. Perfect. Now guys, negative one is called as cathode here. On this particular cathode, as per question, what is getting deposited? Zinc. Here at this negative, at this cathode, what is getting deposited? Silver. And here, what is getting deposited? Over here, copper is getting deposited. Perfect. Copper is getting deposited. Right? And these are the reactions through which these elements are getting deposited. Zinc dye positive from the solution is getting 2 electrons, getting converted into zinc solid, and that zinc solid is deposited here. Similarly, Ag positive in the solution will be getting 1 electron and will be getting converted into Ag solid. That Ag solid is deposited here. Similarly, copper dye positive getting 2 electrons, getting deposited as copper here. Perfect. Now in the question, a current of 2 amperes was passed. Okay, current of 2 amperes is passing in every electrolytic solution. Current of 2 amperes was passed until 1.08 grams of silver was deposited. So as per the question, it is given that 1.08 grams of silver is deposited, right? Is deposited. First, he's asking you how long did the current flow? How long did the current flow? Right? He's asking you T value. How long did the current flow? In what duration of time current flowed? So look at the second cell, my dear students. In this second cell, if I use the Faraday's first law, I can say in the second cell, mass of silver deposited has to be equal to equivalent mass of silver multiplied by I multiplied by T divided by 96500. Now what is the mass of silver deposited as per the question? It's 1.08 grams is equal to equivalent mass of silver is molar mass of silver divided by n factor of silver. N factor of silver, electrons exchanged divided by stoichiometric coefficient, that's 1. Multiplied by what? Multiplied by 96500. Now I, current is 2 amperes multiplied by time. So one equation, one unknown. Can't you calculate T from here? T can be calculated. And as far as I remember, T value will be something 482.5 seconds. Right? So this is the time duration in which current has to flow. Right? In which the current has to go into the solutions. So the question was asking how long did the current flow? Current has flown this long, 482.5 seconds. Number one. Number two, what mass of copper and zinc was deposited? What mass of copper and zinc was deposited? Now use Faraday's second law. What Faraday's second law states? Faraday's second law states that the gram equivalents deposited or liberated at every electrode will be the same, right? So first of all, I'll write like this. Gram equivalents of zinc, that is mass of zinc, divided by equivalent mass of zinc. Gram equivalence of zinc deposited has to be equal to gram equivalence of copper deposited. Sorry, gram equivalence of silver deposited, which is mass of silver divided by equivalent mass of silver. Right? Gram equivalence of zinc deposited should be equal to gram equivalence of silver deposited. Correct? Gram equivalence of zinc deposited is mass of zinc deposited divided by equivalent mass of zinc. Gram equivalence of silver deposited is equal to mass of silver deposited divided by equivalent mass of silver. Now, dear students, have a look. What is the mass of zinc which is being deposited? That's something which has to be calculated. Divided by equivalent mass of zinc is molar mass of zinc divided by n factor of zinc. N factor of zinc is 2 here. Is equal to what is the mass of silver which is being deposited? 1.08 grams as per the question. Divided by equivalent mass of silver, that is molar mass of silver divided by n factor of silver. So from this particular equation, you can easily calculate the mass of zinc which is deposited, and that too the answer will be in grams. Correct? Similarly, after this, once you get the mass of zinc deposited, you can equate gram equivalence of Ag with gram equivalence of silver. Sorry, gram equivalence of Ag with gram equivalence of copper. From there, you can calculate the mass of copper deposited. Is this question clear now? Is this question clear? So T value is 482.5 seconds. Mass of zinc deposited is 0.325. Mass of copper deposited you can calculate through this particular equation. You have just equated the gram equivalence of Ag deposited with the gram equivalence of copper deposited. That's all. Is this clear to everyone? Is that clear to everyone, people? Perfect. So I believe you can solve the Faraday's first law and second law electrolysis questions easily. Now comes one more part of the chapter, that is electrolytic conductance. Electrolytic conductance. This is something important. This is also important. So have a look, people, what it means, what kind of questions can be asked. Just a second, let me see whether I have added questions here or not. These questions are added. Okay. So my dear students, let me mark the heading as terminologies involved. Terminologies involved in electrolytic conductance. Terminologies involved in electrolytic conductance. Or let me just write terminologies involved in electrolytic conductor. You can also call it as conductivity cell. You can also call it as conductivity cell. Now, what this conductivity cell, first of all, is all about. Try to understand what exactly I'm going to talk about. Yeah? Have a look, people. Since we have discussed the electrolytic cell, okay? Again, I'm going to make the electrolytic cell here. Again, I'm going to make the electrolytic cell. Try to understand, guys. This is important. See, this is first of all. Let me make the electrolytic cell here. This is one container. This is one container. And my dear students, in this particular container, what do we have? Imagine that in this particular container, we have got an electrolytic solution. There is electrolytic solution in the container. So in short, I'll say there is electrolyte in the container. There is electrolyte in the container. Which electrolyte? Let's call this as AB electrolyte. There is AB electrolyte in this particular container. Okay. Now what exactly I'm doing? I'm going to place two electrodes here, right? I'm going to place two plates, basically. Two metal plates I'm placing, which are your electrodes. So here, this is your one metal plate, which works like one electrode, right? Similarly, this is one more. This is one more metal plate, which works like one more electrode. Perfect. I've taken two electrodes here. Now, my dear students, you are connecting these electrodes with the help of battery. With the help of battery. This electrode, this plate got the negative charge. This plate got the positive charge. Correct? Now, my dear students, first of all, imagine. Can I say this is the part of the electrode which is in contact with the solution? Yes, this is the part of the electrode which is in contact with the solution. So basically, this is the part of the electrode which is dipped into the solution. Similarly, this is the part of the electrode which is dipped into the solution as well. Perfect. My dear students, let me make one diagram here. Have a look. Let me connect this with this. Let me connect this with this. Let me connect this with this. And let me connect with this with this. Do you see any diagram here? Do you feel something different here? Do you feel something different here? Try to understand. Just a second. Just a second. What did I get? What did I get? What did I get? It's a cube. It's a cube, right? What this cube is containing basically? What is present inside this cube? What is present inside this cube? Can I say in this cube, electrolytic solution is present? Basically, a solution is present which contains electrolyte in this cube. Let me take this cube out from the container. Imagine I'm taking this cube out of the container. When I take the cube out of the container, the cube will look like this. Let me show it to you. I've taken the cube out of the container. The cube is looking like this, right? What is this particular one? It is the part of the plate. It is the part of the electrode. It is the part of the electrode which is inside the solution. This is the part of one more electrode which is inside the solution, right? This electrode carries negative. This electrode carries positive. And in between these electrodes, what do I have? I've got a solution which contains an electrolyte, okay? Right? In this cube, you've got an electrolytic solution. Perfect. Which electrolyte I had taken? AB. So basically in this cube, what you will find? In this cube, you will find A positive ions and B negative ions, right? First of all, my dear students, this particular cell which I made over here, this particular cell is something which I call as conductivity cell. This is something which you call as conductivity cell, correct? Yeah. This is something which I call as conductivity cell. Now, my dear students, let me assume certain things. Let's assume the distance between these two electrodes. Let's assume the distance between these two electrodes is L centimeter. Let's say this area of cross-section of the electrode, that area of cross-section of the electrode which is inside the solution, right? That means this one. This area of cross-section of the electrode which is inside the solution, right? Let's call this as A centimeter square. A centimeter square is the area of cross-section of the electrode which is inside the solution, which is in contact with the solution. Yeah? So this particular cell is something which you call as conductivity cell. Now tell me one thing. This particular plate carries negative charge. This particular plate carries positive charge. Can I say this negatively charged plate is going to attract B negative towards itself? Absolutely. And this positively charged plate is going to attract, negatively charged plate is going to attract A positive towards itself, correct? And this positively charged plate is going to attract B negative towards itself. Now tell me one thing. When A positive will be moving towards negatively charged plate, when this A positive will be moving towards negatively charged plate, during the moment of A positive, can I say there will be some B negatives which will be attracting the same A positive towards itself? Yeah? Similarly, when this B negative will be going towards positively charged plate, when this B negative will be going towards positively charged plate, during its moment, can I say there will be some A positive which will be attracting this B negative towards itself? Absolutely. Do you see any obstruction in the movement of the ions? Absolutely, there is obstruction in the movement of the ions. And that obstruction in the movement of the ions, that is the reason why we say this particular electrolytic solution shows the resistance. So what is the resistance of this cell? It is simply the obstruction during the movement of the ions. Right? What is the resistance of this particular cell? It is the obstruction during the movement of the ions, when the ions are moving towards the respective electrodes. Perfect? So my first terminology, my dear students, that is resistance. That is resistance, which is denoted by R. Which is denoted by R. I'm not going to write its definition because you already know it. Obstruction in the movement of the ions. Right? How do you calculate this R? Tell me that. How do you calculate this R? You know it already. R is equal to rho L by A. R is equal to rho L divided by A. Perfect? R is equal to rho L by A. If I ask you, first of all, what are the units of resistance? Resistance units are ohm. Resistance unit is ohm. Right? How do you represent it? This is how you represent it. Right? This is how you represent it. Clear to everyone? Now, my dear students, in this particular expression, what did we get here? We got this term rho. What is rho? Rho is called as resistivity. Rho is called as resistivity. Resistivity is your rho. So tell me this rho. Can I say rho is equal to RA divided by L? Resistivity rho is equal to RA divided by L. Resistivity rho is equal to RA divided by L. How do you define this resistivity first of all? How do you define this resistivity? How do you define this resistivity? Understand. My dear students, imagine that the area of the cross section A is 1 centimeter square. This particular area, imagine it's 1 centimeter square. Imagine that the distance between the electrodes is 1 centimeter, right? Distance between the electrodes is 1 centimeter. If this cross section area is 1 centimeter square, distance between them is 1 centimeter. Can you let me know what will be the volume of this cube? Volume of this cube will be 1 centimeter cube. volume of this cube will be 1 centimeter cube. This is the volume of the cube right now. Tell me one thing. When A is equal to 1 centimeter square, L is equal to 1 centimeter, can I say at that point of time, your rho is basically equal to R? Can I say your rho is equal to R? Perfect. Can I say resistivity is basically the resistance? Resistivity is basically the resistance. It is basically the resistance shown by this particular electrolyte. When the distance between these plates is 1 centimeter and the dipped area of cross section, that is 1 centimeter square. Or I can define it like this as well. Since the volume of the cube is 1 centimeter cube, if the volume of the cube is 1 centimeter cube, if I ask you, what is the volume of the electrolytic solution in this container? I'll say volume of the electrolytic solution in the container right now is 1 centimeter cube. I'll say resistance shown by 1 centimeter cube of electrolytic solution. Resistance shown by 1 centimeter cube of electrolytic solution, right? That's something which I call as resistivity. Perfect. Right? So it is the resistance. It is the resistance shown by what? By 1 centimeter cube of electrolytic solution. Can you let me know what will be the units of resistivity? Units of resistivity, tell me that. R is ohm, A is centimeter square, this is centimeter. So it has to be ohm centimeter. This is basically the unit of resistivity, ohm centimeter. Clear? So this was my second terminology, that is resistivity. Talking about my third terminology. Just a second. My third terminology is, it is conductance. It is conductance. Conductance is basically represented by G. How do you define this conductance? Conductance is defined simply as inverse of resistance shown by the conductivity cell. Right? Inverse of resistance. Now tell me one thing. 1 divided by R is rho, L divided by A. So this is A here. Perfect. This is A here. So my dear students, tell me just one thing. Look at this particular expression. Okay. Let me tell you the units of this conductance. It is 1 by R. The unit of conductance is going to be, either you'll write ohm inverse, or you'll write mho mho, or you will write it as M. This is the unit of conductance, right? And Simon, it's denoted by S. That's all. Okay. Now similarly, my fourth terminology, that is conductivity. Conductivity is represented by kappa, right? Now the point is, how do you define this conductivity? How did we define conductance? Conductance was inverse of resistance. So how do I define conductivity? Conductivity, or you call it as specific conductance. You call it as specific conductance. Tell me, how do you define it? Specific conductance is nothing. It is inverse of I'm sorry guys, I think I'm going to fall ill. I think there is going to be cold cough soon. Okay, conductivity. How do we define conductivity? It is defined as inverse of resistivity. Inverse of resistivity. Now tell me one thing. 1 divided by, what is rho exactly equal to? Rho is equal to RA divided by L. Rho is equal to RA divided by L. So this is R, this is A, and this is L here. This is L here, right? You can write it like this. 1 divided by R multiplied by L by A. Perfect. This is one of the expressions which I would want you guys to remember, because I'll be using frequently this expression in the questions. Your conductivity kappa, that's equal to 1 divided by R multiplied by L by A. 1 by R multiplied by L by A. Second thing guys, have a look. I'm talking about conductivity, specific conductance. That is your kappa. That's your kappa. So kappa is equal. 1 by R is something which you call as conductance. L by A is something which you call as cell constant. This is conductance. This term is called as cell constant, right? So I'll write something like this. Conductivity. Conductivity is always equal to conductance. Conductance multiplied by what? Multiplied by cell constant. Multiplied by cell constant, right? Your cell constant is what? Your cell constant is L by A. This is cell constant, this is conductance, and this is conductivity. Now, if I ask you what are going to be the units of conductivity? Units of conductivity. Say, conductivity is equal to conductance multiplied by cell constant. So, units of conductivity is going to be, this is conductance. You can write it as Simon. Cell constant. This is centimeter square. So, it's going to be centimeter inverse. So you can write it as Simon centimeter inverse. It is basically the unit of what? It is the unit of conductivity, right? Perfect. It is the unit of conductivity. Simon centimeter inverse. Perfect. Now, my dear students, one more thing. One more important thing. Before talking about the other terminologies, one more important thing which you should remember from now on. Imagine this is your one electrolytic solution. This is your one more electrolytic solution. Okay? Two electrolytic solution I have in two containers. Right? Imagine the resistance of the first solution is Ra, the resistance of the first solution is Rb. Right? Imagine the conductance of the first solution, conductivity of the first solution is Ka and conductivity of the second solution is Kb. These are two solutions. Solution number one, solution number two. Now what you are doing, you are mixing it, you are adding them into a final container. So in this final container, we got 1 plus 2. Perfect. You got 1 plus 2. Now, my dear students, remember one important thing. You are not going to say resistance of the final solution is equal to Ra plus Rb. This is a wrong statement. You are not going to do the question in this format, but you will do the question in terms of conductivity. You will say conductivity of the final solution, that is equal to Ka plus Kb. You will solve the question in terms of conductivity, not in terms of resistance, right? You take a note of this point. It's important. From this particular point, you'll get one question. From this particular point, you'll get one question. If you are adding two solutions, having the resistance Ra, Rb, conductivity kappa I, kappa B, right? The final solution which you get, you are not going to say its resistance is Ra plus Rb. You are going to solve the question in terms of conductivity. You can write conductivity as conductivity of the final solution as conductivity of A plus conductivity of B. I mean conductivity of A plus conductivity of B. Yeah? Right? Now, guys, before doing the other stuff, let me talk about one more important terminology. What is that? That is molar conductivity. Molar conductivity. Molar conductivity is represented by lambda m. Molar conductivity is represented by lambda m. Let me first of all write its definition, then I'll make you understand. Molar conductivity lambda m, it is defined as the conductance. The conductance shown by all the ions, the conductance shown by all the ions when 1 mole of electrolyte is present. When 1 mole of electrolyte is present in a given volume of solution. In a given volume of solution. Try to understand what it means exactly. See, guys, few minutes back, we made a conductivity cell here. Imagine this is the conductivity cell, okay? Imagine this is the conductivity cell. Can I erase all this part? Can I erase all this part? Say yes or no. I just need some space here. Can I erase? Okay, leave it as such. I'm erasing this part. I hope you got to know how this conductivity cell was made. I'm erasing this part. All right. See, guys, there is something important which I'm going to discuss with you now. This is your conductivity cell, and this conductivity cell, what is there in this conductivity cell? Electrolytic solution, correct? Imagine volume of the electrolytic solution, volume of the solution here in the container is V centimeter cube. It can be anything. 10 centimeter cube, 1000 centimeter cube, 50 centimeter cube, whatever. This is the volume of the solution, V centimeter cube. I'm assuming that in a given volume of solution, I'm assuming that in a given volume of solution, 1 mole of electrolyte is present. I'm assuming in a given volume of solution, 1 mole of electrolyte is present. So 1 mole of electrolyte is present in a given volume of solution. My dear students, whenever 1 mole of electrolyte is present in a given volume of solution, the conductance of all the ions shown at this particular point of time is something which you call as molar conductivity. So molar conductivity, it is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. I hope it's clear. It is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. Correct? Now guys, I'm directly going to give you the result. I'm not deriving the result, I'll be directly giving you the result. Molar conductivity of the solution is always equal to kappa multiplied by 1000 divided by molarity of the solution. This is the result which you guys will be using to calculate molar conductivity of the solution. When you have to calculate molar conductivity in Simon centimeter square per mole. When you have to calculate the molar conductivity in Simon centimeter square per mole, this is the equation which you will be using. Kappa multiplied with 1000 divided by molarity of the solution. For example, you have to calculate the molar conductivity in Simon meter square per mole. If you have to calculate the molar conductivity in Simon meter square per mole, this is not the relation which you will be using. You will be using the relation like this. Kappa conductivity divided by 1000 multiplied by molarity of the solution. Perfect. My dear students, I want you guys to remember these two expressions. Is this clear? I hope you got to know what molar conductivity exactly is. Say yes or no in the chats. Say yes or no in the chats. Okay. All right. There is one more similar terminology that's called as equivalent conductivity. Which is represented by lambda EQ. Now, how do you define this equivalent conductivity? Let me write its definition. It is similar. Equivalent conductivity is defined as the conductance shown by all the ions when 1 gram equivalent of electrolyte is present in a given volume of solution. The conductivity cell which I took few minutes back. Imagine in the given volume of solution, there is 1 gram equivalent of electrolyte present. When 1 gram equivalent of electrolyte is present in a given volume of solution, whatever will be the conductance shown by ions at that point of time in the conductivity cell, that is something which I'll be calling as equivalent conductivity. As simple as that. There is one difference only. Instead of 1 mole of electrolyte, you are using 1 gram equivalent of electrolyte, nothing else. The rest, everything is same. Okay? Only difference is instead of 1 mole of electrolyte, you are using 1 gram equivalent of electrolyte. That's it. Now, the point is, how do we calculate it? Lambda EQ, one of the result. Kappa multiplied by 1000 divided by normality. This is the equation which you will be using to calculate the equivalent conductivity. In Simon centimeter square per equivalent. If you will have to calculate equivalent conductivity under these units, this is the expression which you will be using, right? But if you will have to calculate the equivalent conductivity in Simon meter square per equivalent, what is the formula which you will be using? It's going to be kappa divided by 1000 multiplied by normal. Perfect. Correct. Now, my dear students, if I ask you, what is going to be the relation between molar conductivity and equivalent conductivity? If I ask you what is the relation between molar conductivity and equivalent conductivity? Molar conductivity and equivalent conductivity. What is going to be the relation? See, since one of the relations I told you, lambda EQ is equal to kappa multiplied by 1000 divided by normality. This is one of the results which I told you, right? Which I gave you. Now tell me one thing. And I write it like this, kappa multiplied by 1000 divided by. Instead of normality, I'll write molarity multiplied by n factor. You know it? Normality is equal to molarity multiplied by n factor of solute. Solute is your electrolyte. So normality is molarity of the solution multiplied by n factor of electrolyte. Correct? This particular term, my dear students, this particular term, what do we call this as? We call this as lambda m. So it is going to be lambda m divided by n factor. So from this particular result, you got equivalent conductivity is always equal to molar conductivity of the solution divided by n factor of electrolyte. N factor of electrolyte. This particular result is also important. Is this clear? Is this clear to everyone? Let me know once in the chat quickly. Is it clear? Perfect, right? Let's try to do a few questions on the same concepts which we have discussed. Then we'll move on to a few other concepts too. Look at this particular question. Look at this particular question, guys. The specific conductance means conductivity, of 0.1 molar solution of MgCl2 is given. The cell electrodes of 1.5 centimeter square area and placed 0.5 centimeters apart in the solution. How much current should flow if potential difference between electrodes is 5 volts? What are we supposed to calculate? We are supposed to calculate current, right? We are supposed to calculate current. Use the Ohm's law. I is equal to V divided by R, right? Potential difference is 5 volts divided by resistance of the cell we do not know. So we have to calculate resistance of the cell, right? We have to calculate the resistance of the cell. Few minutes back, I gave you one result, important result I told you at that time. That is kappa is equal to 1 divided by R multiplied by L by A, right? Now tell me, can't you calculate R from here? 1 divided by kappa multiplied by L by A. It's going to be 1 divided by. This is specific conductance. How much is it? It is 0.009 multiplied by distance between electrodes. Distance between electrodes is 0.5 centimeter divided by area of cross section of the electrodes. That is 1.5 centimeter square. So from here, you can easily calculate your what? Resistance. Once you get the resistance value, put the value of resistance in this particular equation, you'll get the current. Are you getting this? Are you getting this, people? Right? So resistance is coming as 0.075 ohm and current is coming out to be 0.135 ampere. I believe it's clear. I believe it's clear to everyone. Okay? Let's solve one more question. Let's solve one more question. Look at this. You can easily solve this as well. Now these are simple questions. The resistance of 0.01 normal solution of an electrolyte is 210 ohm. Resistance is given. Cell constant is given. Calculate conductivity and equivalent conductivity of the solution. So we have to calculate conductivity as well as equivalent conductivity. Conductivity is kappa, which is equal to 1 divided by R multiplied by L by A, right? So kappa is going to be equal to 1 divided by R. R is resistance, which is 210 ohms. L by A is the cell constant. Cell constant is given to us as 0.88 centimeter inverse, right? When you solve this, you get the answer in Simon centimeter inverse. This is your conductivity. This was the first question. Second is calculate equivalent conductivity. Equivalent conductivity is equal to, you have to calculate equivalent, by the way, we have to calculate equivalent conductivity in Simon centimeter square per equivalent. These are supposed to be the units in the question. So lambda AQ is going to be kappa multiplied by 1000 divided by normality, right? Divided by normality. Perfect. Kappa you have already calculated. Normality of the solution is also given. Put it here and get the equivalent conductivity of the solution in Simon centimeter square per equivalent. Done. These are just the formula based ones, right? Just the formula based ones. So kappa you have calculated, put it here and get the equivalent conductivity. That's it. Nothing else to do. These are the basic questions now. These are the basic questions now. Okay. Let's have a look on this question. The equivalent conductivity. The equivalent conductivity of 0.1 normal. Solution of CaI2 is 100. And its units, you already know, it is Simon centimeter square per equivalent. If the cell constant is this much, how much current will flow when the potential difference between the electrodes is 5 volts? Right? Can you give it a try? Can you give it a try? See guys, what are we supposed to calculate? Again, we have to calculate current. Current is nothing, it's potential difference, voltage divided by R, right? Well, potential difference is given to us as 5 volts again. Now, we have to calculate R. How do we calculate R exactly? How do we calculate R exactly? How do we calculate R exactly? Quickly, how do we calculate R? I told you a few minutes back only, your kappa is equal to 1 divided by R multiplied by L by A. Correct? So R you can calculate as 1 divided by kappa multiplied by L by A. Perfect. Now, as per the question, this particular term cell constant, this is given to me, correct? But this kappa is not given to me. So I have to calculate kappa as well. I have to calculate kappa as well. From where I calculate the conductivity. For that purpose, equivalent conductivity is given. Equivalent conductivity is given to me as 100 Simon centimeter square per equivalent. This is the equivalent conductivity which is given to me. Now you know, equivalent conductivity is equal to kappa multiplied by 1000 divided by normality, right? This is equal to 100. Tell me one thing. Is the normality of the solution given to me? Yes, it's given to me, right? If normality is given, from here, it is given to me as 0.1. From here, you can calculate kappa. Conductivity can be calculated. If conductivity is calculated, put it here. Cell constant already you know, you'll get the resistance. If you got the resistance, put it here, you'll get the current. That's something which you were supposed to calculate. So, let's talk about first of all the effect of dilution. Effect of dilution on conductivity, molar conductivity, and equivalent conductivity. What happens to conductivity, molar conductivity, and equivalent conductivity with dilution? Let's have a look, people. All right. See, first of all, if I particularly talk about conductivity, how do you exactly define conductivity? We have already defined it. I hope you remember. How did we define conductivity? Conductivity was defined as, the conductance shown by 1 centimeter cube of an electrolytic solution, right? The conductance shown by 1 centimeter cube of electrolytic solution, correct? Try to understand what exactly I'm going to say, my dear students. First of all, I'm going to make the conductivity cell again. So first of all, this is the cube which I'm making over here. From this particular cube, you'll get the idea what happens to conductivity, okay? So imagine this is the conductivity cell which I'm again making, and these are the plates. These are the plates which are basically inside the electrolytic solution. These are the plates which are basically inside the electrolytic solution. I hope you remember from where we got this conductivity cell, right? Now, my dear students, inside this particular cube, we have got the electrolytic solution. I hope you remember. This is something which we have already discussed. Let's call this as the negatively charged plate. Let's call this as the positively charged plate. Perfect. If you remember from where we got this cube, we got this cube from the electrolytic cell basically. We took this cube out. And this shaded part, what is this shaded part? It is the part of the electrode that is inside the solution. It is the part of the electrode that is inside the solution. Actually, this is the actual size of the electrode. This is basically the actual size of the electrode, right? This is the actual size of the electrode, and this part of the electrode is inside the solution. I hope this is clear. Okay. And my dear students, if you remember, the distance between these two electrodes is represented by what? It's represented by L centimeters. And that area of cross section which is inside the solution, that is represented by A centimeter square. Perfect. Perfect. My dear students, how do we define the conductivity? It is the conductance shown by 1 centimeter cube of the solution. It is the conductance shown by 1 centimeter cube of the solution. Imagine the volume of this particular solution, the volume of this electrolytic solution, for example, is 100 centimeter cube. It is 100 centimeter cube. Let's assume that in this 100 centimeter cube electrolytic solution, let's assume that there are, for example, some 500 ions present. There are some 500 ions present. Okay. So if in 100 centimeter cube, there are 500 ions present, can you let me know in 1 centimeter cube, how many ions will be present? 500 by 100, that comes out to be 5 ions. So if in 100 centimeter cube solution, there are 500 ions, that means in 1 centimeter cube of solution, there are 5 ions present. Perfect. So that means whatever will be the value of conductivity, that is due to these 5 ions. Correct? Now try to understand. Imagine that you are adding some extra solvent here. So you are doing the dilution. That means you are doing the dilution. You are adding some extra solvent here. My dear students, on adding the extra solvent, what will happen to the volume of solution? Volume of solution will increase. Initially, the volume of solution was 100 centimeter cube, right? Now, due to dilution, let's assume that the volume of the solution reached 1000 centimeter cube. Imagine due to dilution, volume of the solution reached 1000 centimeter cube. What did we do? We just added solvent. Did I do anything to the solute? Did I add some more electrolyte here? No. The amount of electrolyte in the container is same. It is just I'm adding more solvent. Okay. After the addition of more solvent, this volume of the solution increased. Volume of the solution increased to 1000 centimeter cube. Now, in 1000 centimeter cube, how many total ions will be there? Total ions will be still 500 only. Because I did not add some electrolyte. I did not add more electrolyte. Electrolyte is same. Now tell me, this was the case of before dilution. And this is the case of after dilution. Tell me one thing. If in 1000 centimeter cube, there are 500 ions. Tell me, in 1 centimeter cube of solution, how many ions will be there? How many ions will be there? Let me not call it as 5000. Let me call it as, just a second, otherwise calculation will be wrong. Let's say after dilution, the volume of the solution is 500 centimeter cube. After dilution. So 500 centimeter cube of solution contains 500 ions. So 1 centimeter cube of solution will contain 1 ion. 1 centimeter cube of solution will contain 1 ion. My dear students, can I say, due to dilution, due to the addition of extra solvent, the number of ions per unit cube of the solution, the number of ions per unit cube of the solution decreased? Can I say something like that? Initially, before dilution, in 1 centimeter cube of solution, there were 5 ions, right? So conductivity was due to 5 ions. Now, due to dilution, volume of the solution increased. Now, for example, volume of the solution now is 500 centimeter cube. Now, in 500 centimeter cube, I must say there are still 500 ions only, right? So in 1 centimeter cube of solution, there is 1 ion. So due to dilution, what is happening? Number of ions per unit volume. Number of ions per unit volume were initially 5. And now due to dilution, number of ions per unit volume is 1. So I would say due to dilution, number of ions per unit volume of the solution decreases. Right? I'll say due to dilution, I would say number of ions in 1 centimeter cube of solution, 1 centimeter cube of electrolytic solution, that decreases. And my dear students, it's understood, if number of ions in 1 centimeter cube of solution decreases, what will happen to conductivity? Conductivity automatically will decrease. So do remember, conductivity of the electrolytic solution, it decreases with dilution. Is this point clear to everyone? This was our first point. Okay? Let me know once in the chats if this point is clear. Number of ions in 1 centimeter cube of solution are decreasing. If number of ions are decreasing, that automatically tells you that conductivity of the solution is decreasing, right? Because what is conductivity? It is the conductance shown by all the ions in 1 centimeter cube of solution. If in 1 centimeter cube of solution, number of ions are decreasing due to dilution, that automatically tells you the conductivity is decreasing with the dilution. Perfect. So this was your conductivity part. Now, let's have a look on molar conductivity now. What happens to the molar conductivity? What happens to the molar conductivity with dilution? What happens to the molar conductivity with dilution? First of all, how do you define the molar conductivity? Do you remember? How do we define the molar conductivity? It is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. I hope you remember. Let's say this electrolytic solution which is there in the container. Let's say volume of this electrolytic solution is, for example, V centimeter cube. Volume of this particular electrolytic solution is V centimeter cube. And in this given volume of solution, let's assume that there is 1 mole of electrolyte present. So I'm assuming 1 mole of electrolyte is present in this given volume of solution. So whatever conductance this particular solution shows right now, that is something which I call as molar conductivity. Now, what happens to molar conductivity with the dilution? That is the discussion. Imagine that in this particular solution, the electrolyte which we have used, for example, that is a strong electrolyte. I'm assuming that in this particular given volume of solution, there is 1 mole of strong electrolyte present. Strong electrolyte is the one which gets completely dissociated into its ions. So if 1 mole of strong electrolyte is in this particular solution, that 1 mole of electrolyte would have got completely converted into its ions. Now, my dear students, what all types of ions will be there in the container? There will be cations and anions in the container. There will be cations as well as anions in this particular container. Perfect. Now, imagine you are doing dilution. If you are doing dilution, that means you are adding some extra solvent. If you are putting some extra solvent in this solution, what is happening to the volume of solution? Volume of the solution is increasing. If volume of the solution is increasing, the distance between the oppositely charged ions, that will increase. And if the distance between oppositely charged ions increases, the force of attraction between them decreases. And if the force of attraction between these ions is decreasing due to dilution, I'll say due to dilution, since force of attraction between these ions is decreasing, I'll say due to dilution, the ions will start moving freely comparatively. And more the movement of ions, More the moment of ions, more has to be the molar conductivity. Done and dusted, right? Clear, guys? Clear? So I had 1 mole of strong electrolyte in this solution. And whatever conductance this solution was showing, that was called as molar conductivity of this solution. Now you are adding some extra solvent. Due to the addition of extra solvent, what is happening to the distance between the ions? It is increasing. Force of attraction between the ions, it's decreasing. Now the ions can comparatively move freely, right? Ions can comparatively move freely. If the ions can comparatively move freely, I would say molar conductivity of this solution automatically increased, right? So do remember, in case of strong electrolytes, with dilution, molar conductivity of the strong electrolyte, that increases. What is the reason? Reason is the distance between the ions, that increases, right? I'll say the reason is distance between the oppositely charged ions, that increases. Hence, force of attraction between the ions decreases, and eventually the ions start moving comparatively freely. Ions start moving comparatively freely. I hope this point is clear to everyone. Is this point clear to everyone? Quickly in the chats. Yeah. Now, my dear students, as I told you, with dilution, molar conductivity completely increases. It keeps on increasing. With dilution, molar conductivity keeps on increasing. So if I keep on doing the dilution, if I keep on adding the solvent, molar conductivity of this solution will keep on increasing. Molar conductivity will keep on increasing. And my dear students, there will be a time when this particular solution shows maximum molar conductivity. And when this particular shows maximum molar conductivity, when the distance between the ions will be infinite, at that time, there'll be no force of attraction between the ions. At that time, ions can completely move freely. Okay? So with dilution, molar conductivity of this solution, of this electrolytic solution, it is increasing, right? If you keep on continuously doing the dilution, molar conductivity will keep on increasing. The ions will go far, right? Okay, there will be a time when these ions will be at infinite distance apart. At that point of time, force of attraction between the ions will be 0. So at that point of time, there is maximum free movement of these ions. So if there is maximum free movement of ions, I'll say molar conductivity value of this particular solution will be maximum. And at that point of time, when the molar conductivity of the electrolytic solution attains its maximum value, we say that dilution at which the molar conductivity of the solution attains its maximum value, that dilution is something which we call as infinite dilution. Let me know once in the chats if you got the idea of what infinite dilution is. So I'll write it over here. If I keep on doing the dilution continuously, then there'll be a point which is what we call as infinite dilution. There'll be a time which is what you call as infinite dilution. So at infinite dilution, distance between the ions is infinite. Force of attraction 0. Ions will move freely. I'll say lambda m, molar conductivity, attains its maximum value. And the maximum value of molar conductivity. Is something which you call as molar conductivity at infinite dilution, or it is represented like this. Lambda m infinite. Perfect. Is this clear? Same thing happens to equivalent conductivity as well. Equivalent conductivity also increases with the dilution. And at infinite dilution, equivalent conductivity attains its maximum value, which is what you call as equivalent conductivity at infinite dilution. Right? Perfect. I'll say equivalent conductivity also increases and hence attains its maximum value, which is what you call as equivalent conductivity at infinite dilution, or you can represent it like this. Perfect? Perfect, guys? So in case of strong liquids, if the electrolytic solution contains a strong electrolyte, with dilution, its molar conductivity as well as equivalent conductivity increases because ions, they go far. They go far. So when you keep on doing the dilution continuously, at infinite dilution, there'll be maximum distance, infinite distance between the oppositely charged ions in the container, due to which no force of attraction between the ions, due to which ions are moving freely. So the maximum molar conductivity value or the maximum equivalent conductivity value will be there at infinite dilution. Perfect. My dear students, if you want to understand it with the help of graph, if I plot a graph for a strong electrolyte, and the graph is between lambda m versus under root of C, where C is the concentration of electrolyte in the container. Where C is the concentration of electrolyte in the container. So first of all, what is C? Concentration. Concentration means moles per unit volume. Perfect. Tell me one thing. This graph I'm plotting for the strong electrolyte first of all. I'm plotting for the strong electrolyte. Okay. At this particular point of time, what is root C value? Root C value here is 0. At this point, root C value is 0. If root C is 0, that means C is 0. That means C is 0. When will be C 0? C will be 0 at infinite dilution, when volume of the solution, volume of the electrolytic solution had become infinite, right? So this point represents your infinite dilution. And infinite dilution, molar conductivity of the strong electrolyte, right? Molar conductivity of the electrolytic solution that attains its maximum value. And that maximum value is lambda naught m. So at this point represents your infinite dilution. This point represents infinite dilution. At infinite dilution, molar conductivity attains its maximum value, which is lambda naught m. Let's assume that this point is lambda naught m. This point is lambda naught m. Now tell me one thing. This is infinite dilution, at which volume of solution had become infinite. Now, if you go in this direction, in this positive x-axis direction, what is happening to root C value? If you go in this direction, root C value is increasing. If root C is increasing, that means C is increasing. If root C is increasing, that means C is increasing. C increasing means volume of the solution is decreasing. At this point of time, volume of the solution was infinite. Now you are going in this direction. C is increasing, right? That means V is decreasing, volume of the solution is decreasing. Initially, the volume of the solution was infinite. Now, volume of the solution is decreasing. If volume of the solution is decreasing, that means the oppositely charged ions in the container, they are coming closer. If they are coming closer, distance between them decreases. If distance between the oppositely charged ions decreases, force of attraction between them increases. Now the ions cannot move the way they were, right? The way they were moving. Therefore, what will happen to molar conductivity? Molar conductivity will decrease. So, molar conductivity value, it will keep on decreasing with time. Perfect. But this particular graph, it is valid for what? It's valid for strong electrolyte. Okay. Now tell me one thing. Since this particular graph, can you tell me what will be its equation? Its equation. See, there is an intercept, there is a negative slope. So it will follow this type of the equation. Y is equal to minus mx plus c. This particular graph will follow this particular equation. Y is equal to minus mx plus c. Now along y-axis, what are you plotting? Along y-axis, you are plotting lambda m is equal to minus. M is the slope of the curve. Let's say slope of the curve is represented by a. What is x? Along x-axis, you are plotting root c. And what is this particular c? C is the intercept. Intercept is the distance from here to here, which is lambda naught m. This is the equation which correctly represents the behavior of strong electrolyte when the behavior of molar conductivity of strong electrolyte when it undergoes dilution. Perfect. This particular equation is valid for a strong electrolyte when it undergoes dilution. I hope this is clear. Right? I hope this is clear. Now, my dear students, when you talk about the weak electrolytes, imagine that in this container, you have got a weak electrolyte. Imagine that you have got 1 mole of weak electrolyte. You have got 1 mole of a weak electrolyte in a given volume of solution. Okay? Right? Imagine that you have got 1 mole of weak electrolyte in a given volume of solution. So whatever conductance this particular solution will be showing, what you call as molar conductivity, right? Now, if there is weak electrolyte in the container, what will happen to the dilution? Let's check that too. Let's check that too. For example, there is a weak electrolyte in the container. For example, there is weak electrolyte in the container. If there is weak electrolyte in the container, tell me about weak electrolyte. Weak electrolyte gets partially ionized. That does not get 100% dissociated into its ions. Now, my dear students, with dilution, if you remember, with dilution, degree of dissociation of a weak electrolyte, what happens to it? With dilution, the degree of dissociation of a weak electrolyte, that increases, correct? That increases. With dilution, degree of dissociation of a weak electrolyte, that increases as per Ostwald's dilution law, right? Now, if the degree of dissociation of a weak electrolyte increases, can I say number of ions in the solution, they are increasing? If number of ions in the solution are increasing, I directly say molar conductivity of the solution increases, as well as equivalent conductivity of the solution increases. So molar conductivity as well as equivalent conductivity of the weak electrolytic solution, that also increase with dilution. But the reason is different. Reason here is, as the dilution is done, degree of dissociation of the weak electrolyte increases, more ions will enter into the solution, more the ions, more will be the molar conductivity as well as equivalent conductivity, right? And molar conductivity at infinite dilution, that's what you call as lambda naught m. Similarly, equivalent conductivity at infinite dilution, that is lambda naught eq. Now, my dear students, if you try to draw a graph, between lambda m versus root c for a weak electrolyte, the graph comes like this. It's a hyperbola, right? The graph comes like this. Right? The graph comes like this. Now tell me one thing. At this particular point, root C value is 0. That means C is 0. When is C 0? I told you a few minutes back. When is C 0? C is 0 when volume of the solution is infinite. That means this particular point, it represents infinite dilution. Since I told you with dilution, the degree of dissociation keeps on increasing, right? If you continuously keep on doing the dilution, can I say there will be a time when the weak electrolyte would have got 100% ionized? And that point when the weak electrolyte would have got 100% ionized, that dilution I call as infinite dilution, right? If this point represents infinite dilution, so I would say at this particular point of time, the electrolyte would have got 100% ionized. The electrolyte would have got 100% converted into its ions. So at infinite dilution, there will be maximum ions in the container. So molar conductivity as well as equivalent conductivity would have attained its maximum value, which is what you call as molar conductivity or equivalent conductivity at infinite dilution, right? Perfect. That's why the graph started somewhere here. Now, my dear students, as you go in the right direction, root C is increasing. If root C is increasing, that means C is increasing. If C is increasing, that means volume is decreasing. If volume is decreasing, volume of the solution is decreasing, what does that mean? That means the degree of ionization of the weak electrolyte. What is happening to that? Or let me make it simple. I told you, when you do the dilution of the weak electrolyte, number of ions in the container increases, right? Due to dilution, volume of the solution increases. So in short, I'll say, when the volume of the solution keeps on increasing with dilution, number of ions in the solution keeps on increasing, right? Now the volume of the solution is decreasing. In this direction, volume of the solution is decreasing. If volume of the solution is decreasing, what does that mean? That means number of ions in the solution will be decreasing. If number of ions in the solution are decreasing, I'll say molar conductivity as well as equivalent conductivity, they'll be decreasing also. Perfect. But from this graph, are you able to find the molar conductivity at infinite dilution? See, from this particular graph, you were able to find the molar conductivity at infinite dilution with the help of this intercept. But in this particular curve, do you have any intercept? There is no intercept. So from this particular curve, which is valid for a weak electrolyte, from this particular curve, you cannot calculate the molar conductivity at infinite dilution for a weak electrolyte. But for strong electrolytes, we can do with the help of the graph, with the help of its intercept. Now the point is how to calculate the molar conductivity and equivalent conductivity at infinite dilution for a weak electrolyte. If it cannot happen through this particular graph, if you are unable to get the molar conductivity at infinite dilution for a weak electrolyte from the graph, if you are unable to do that, then how do we get the molar conductivity at infinite dilution for a weak electrolyte? My dear students, in order to get the molar conductivity at infinite dilution, as well as equivalent conductivity at infinite dilution for a weak electrolyte, in order to get those values, I'm going to introduce one more topic, that is what you call as Kohl-Royce law. That's what you call as Kohl-Royce law. Kohl-Royce law. So what this Kohl-Royce law exactly states? Say, you can read its definition. This law states that the equivalent conductivity of any electrolyte at infinite dilution is the sum of equivalent ionic conductivities of cation and anion given by the electrolytes at infinite dilution. What it means exactly? What it means exactly? What it means? Let's try to understand. First of all, whenever there is infinite dilution, at infinite dilution, 100% electrolyte is ionized. At infinite dilution, the distance between the oppositely charged ions in the solution, that is infinite. Force of attraction between the oppositely charged ions, that is zero. So that means I can say at infinite dilution, ions, they move freely, right? They move freely. So at infinite dilution, the ions move freely. This is something which is understood. Now, my dear students, try to understand. Try to understand what exactly I'm going to say. Try to understand what exactly I'm going to say. Say, for example, in the conductivity cell, let's say you have got an electrolyte like NaCl. You have got an electrolyte like NaCl. Perfect, like NaCl. First of all, how this NaCl would have got dissociated? It would have got dissociated as Na positive plus Cl negative. Stoichiometric coefficient 1, here it is 1, here it is 1. Perfect. Now, Kohl-Royce law says that molar conductivity of this NaCl, for example, at infinite dilution is the sum of conductivities of its ions, basically. So basically, since this electrolyte at infinite dilution, it's 100% ionized, right? Number one, it's 100% ionized. There is no force of attraction between the ions. Ions are moving freely. Ions are moving freely. So it is the ions basically which contribute. It is the ions basically which contribute towards the molar conductivity of the electrolyte at infinite dilution. So molar conductivity of the electrolyte at infinite dilution, as per Kohl-Royce law, is the sum of those contributions. Is the sum of those contributions which are made by the ions. What it means? Have a look. Molar conductivity of NaCl at infinite dilution. See, how do you write it as per your Kohl-Royce law? The stoichiometric coefficient here is 1. So write 1 first, then write molar conductivity at infinite dilution for Na positive plus, this is 1 also, right? Molar conductivity at infinite dilution of Cl negative, correct? For example, you have got electrolyte like this. You have got, for example, BaCl2. At infinite dilution, BaCl2, first of all, it would have got completely dissociated into its ions, right? And at the same time, the force of attraction between the oppositely charged ions at infinite dilution will be 0, right? So these ions will be moving freely. Now, as per Kohl-Royce law, lambda naught m of BaCl2, will be equal. The stoichiometric coefficient here is 1. So 1 multiplied by lambda naught m of Ba di positive plus 2 multiplied by lambda naught m of Cl negative. Correct? Perfect. For example, you have got electrolyte like this. Al2SO4 whole thrice. How it would have got dissociated at infinite dilution? It is 2 times Al tri positive plus 3 times SO4 di negative. Now, if you want to write the molar conductivity at infinite dilution for Al2SO4 whole thrice, you can write it like this. Start with 2, then write molar conductivity at infinite dilution for Al tri positive plus 3 times the molar conductivity at infinite dilution for SO4 di negative. Perfect. Can you write these statements for every electrolyte? You should be able to write these particular statements, correct? You should be able to write these particular statements for the electrolytes. Now, my dear students, let me tell you one more thing. Since you are getting the molar conductivities of electrolytes at infinite dilution, like this. If I ask you, how do you get the equivalent conductivity of the electrolyte at infinite dilution? Already, if you remember, I've already discussed one relation with you. Equivalent conductivity is equal to molar conductivity divided by n factor of the electrolyte. We have discussed this relation. Perfect. So, if you get molar conductivity at infinite dilution of the electrolytes, once you get the molar conductivities, you can easily calculate their equivalent conductivities at infinite dilution. So, equivalent conductivity at infinite dilution will be equal to molar conductivity of the electrolyte at infinite dilution divided by n factor of this particular electrolyte, this particular electrolyte. I hope this is clear. I hope this particular statement is clear. Right? I hope this particular statement is clear. Perfect. Perfect, guys. One more thing. For example, I'm writing a statement like this. Let's say I already know equivalent conductivity at infinite dilution of Na positive. Let's say this is something I know. I already know equivalent conductivity of Cl negative at infinite dilution in equivalent conductivities, right? I already know equivalent conductivity at infinite dilution of Ba di positive. These are the terms which I already know, correct? Now, if you want to write directly the equivalent conductivity of NaCl, when you directly want to write equivalent conductivity of NaCl in terms of equivalent conductivity at infinite dilution for their ions, listen to me carefully. Imagine equivalent conductivity at infinite dilution for Na positive, you know, this one you know, right? Now I want you directly to write the equivalent conductivity of at infinite dilution for NaCl, right? That too in terms of the equivalent conductivities of their ions. At infinite dilution. You do not have to talk about these stoichiometric coefficients at that particular point of time. You can directly write lambda naught EQ of Na positive plus lambda naught EQ of Cl negative. Perfect. For example, here I was writing the molar conductivity of BaCl2. I was taking into consideration these stoichiometric coefficients. But if you are directly writing the equivalent conductivity at infinite dilution in terms of the equivalent conductivities of their ions, then you do not have to talk in terms of, you do not have to write the stoichiometric coefficients here. For example, let me make it clear. Let's say I'm writing equivalent conductivity at infinite dilution of BaCl2. If you want to write it in terms of equivalent conductivities of their ions, you have got nothing to do with the stoichiometric coefficients. You'll directly write equivalent conductivity of Ba di positive plus equivalent conductivity of Cl negative. Nothing to do with their stoichiometric coefficients. But if you are writing molar conductivity at infinite dilution for BaCl2, right, you will be writing lambda naught m of Ba di positive plus 2 times lambda naught m of Cl negative. I hope these two statements are clear to you. Yeah? I hope these two statements are clear to you. Perfect, guys? And at the same time, if you directly know the molar conductivity at infinite dilution of an electrolyte, divide it with the n factor of electrolyte, you will get directly the equivalent conductivity of the same electrolyte at infinite dilution. One more important thing. All these things are very, very important, guys. These are very small things wherein majority of the students, they do the mistake. Okay? Perfect. Now, let's exactly get to know how this Kohl-Ross law is, how this is used basically. Where all do we use this Kohl-Ross law? Number one, Kohl-Ross law exactly is used to calculate the limiting molar conductivity of a weak electrolyte. Limiting molar conductivity of a weak electrolyte means Kohl-Ross law is used to calculate the molar conductivity of a weak electrolyte at infinite dilution. Because from the graph, we could not get the molar conductivity at infinite dilution of a weak electrolyte. So it is the Kohl-Ross law which is going to give us, the molar conductivity at infinite dilution of a weak electrolyte. This is the first application. To calculate, you can write it as like this. To calculate the limiting molar conductivity. To calculate the limiting molar conductivity of a weak electrolyte. This is the first application. This is the first application of the Kohl-Ross law. To calculate the limiting molar conductivity of a weak electrolyte. To calculate the molar conductivity at infinite dilution of the weak electrolyte. Okay. Now, how exactly? How exactly? It's simple, guys. Have a look. Understand properly. For example, molar conductivity at infinite dilution for HCl is given to us. Okay. NaCl is also given to us. CH3COO is also given to us. These are few parameters which are given to me. And by looking at these parameters, we have to calculate the molar conductivity at infinite dilution for CH3COH. Correct? How exactly I'll get this particular term from these terms? Now understand. Simple thing it is. Understand it properly. So first of all, lambda naught M of HCl. I can write it as lambda naught M of H positive plus lambda naught M of Cl negative. Correct? Because stoichiometry is 1:1. And this value is already given to me as 426, 7 centimeters square per mole. Lambda naught M of NaCl, I can write it as lambda naught M of Na positive plus lambda naught M of Cl negative. And this particular term is given to me as 126. Lambda naught M of CH3CONa, it is going to be equal to lambda naught M of CH3CO negative plus lambda naught M of Na positive. And this value is equal to 91. So how many equations do I have? How many equations do I have? I have got 3 equations. From these 3 equations, I have to get this particular value, lambda naught M of CH3COH. First of all, how do you break this CH3COH? I say basically I have to get this value, lambda naught M of, I have to get basically the value of lambda naught M of CH3CO negative plus lambda naught M of H positive. Basically, this is the value which I need to get. This is the value which I need to get. Perfect. Now, my dear students, how do you get this value? How do you get this particular value out of these 3 equations? This is equation 1, call this is equation 2, call this is equation 3, right? How do you get it? How do you exactly get it? What do you need exactly? You need lambda naught CH3CO negative and lambda naught H positive. So you need this term and you need this particular term. Perfect. Rest all the terms should get cancelled. Rest all the terms should get cancelled. Perfect. So I'll be adding equation 1 with equation 3 and I'll be subtracting equation 2. I'll be adding 1 with 3 and subtracting 2 at the end. Perfect. If I subtract 2, this becomes minus, this becomes minus, this becomes minus. Perfect. What do I get at the end? I'll say this particular term gets cancelled. This particular term gets cancelled. What do I get at the end? Lambda naught CH3CO negative plus lambda naught. After doing this particular operation, what am I left with? I'm left with lambda naught of H positive plus lambda naught of CH3CO negative. Perfect. Lambda naught H positive plus lambda naught CH3CO negative. What do I call this as? I'll be calling this particular term as lambda naught M of CH3COH. Perfect. How did I get this? By doing this particular operation. Same operation you are going to do with these molar conductivities. So 1 plus 3 minus 2. So 1 plus 3 minus 2. So it has to be 426, 1 plus 3 minus 2. Whatever value you get from here, that is going to give you the molar conductivity at infinite dilution for this particular weak electrolyte. Did you get it? Did you get it properly? Let me know once in the chats quickly, guys. Quickly, everyone. Did you get this particular term? Let me give you one more question. Let me see if you can solve this or not. The question is like this. I'm giving you lambda naught M of NaCl. This value I'm giving you as For example, 126.5 Simon centimeter square per mole. This is the value which I give you. Second value I'm giving you as lambda naught m of HCl. This is something which I'm giving you again. This value is something 425.9 Simon centimeter square per mole. Right? Similarly, I'm giving you one more value. Lambda naught m of NaI. This value is 91 Simon centimeter square per mole. And I'm asking you to calculate lambda naught m for HI. This is something which you are supposed to calculate. Can you give it a try? Can you give it a try? My dear students, same thing you have to do. Same thing you have to do. First of all, lambda naught m of NaCl can be written like this. Lambda naught m of Na positive plus lambda naught m of Cl negative. This particular term I'll be writing as lambda naught m of H positive plus lambda naught m of Cl negative. This particular term I'll be writing as lambda naught m of Na positive plus lambda naught m of I negative. This particular term I'll be writing as lambda naught m of H positive plus lambda naught m of I negative. This is something which is to be calculated. Let's call this as equation 1. Let's call this as 2. Let's call this as 3. From these equations, in total there are 1, 2, 3, 4, 5, 6 terms. Out of 6 terms, from these 6 terms, I should get only lambda naught H positive plus I negative. So there should be only H positive and there should be I negative. Rest all the things should be cancelled out. So what I should be doing? I'll be just doing one thing. I'll do equation 2 plus equation 3 minus equation 1. Let's see what I'll be getting. I'm subtracting equation number 1. So lambda naught Na positive is cancelled. Lambda naught Cl negative is cancelled. So what I'm left with? I'm left with lambda naught H positive plus lambda naught I negative. So I got lambda naught H positive plus lambda naught m of I negative. This is something which I call as lambda naught m of Hi. Now, how did I get this basically? How did I get this? By adding second with third and subtracting first. Adding second with third and subtracting first. Do the same operation with their molar conductivity values. So 2 plus 3. So this plus this minus this. So the answer has to be 425.9 plus 91 minus 126.5. Solve it. Whatever value you get, the answer is going to be Simon centimeter square per mole. This is the molar conductivity at infinite dilution for this particular electrolyte Hi. I hope this is again clear to everyone. So this was the first application of the Kohl-Ross law, right? To get the limiting molar conductivity, to get the molar conductivity at infinite dilution for a weak electrolyte, correct? Now what about its second? What about its second application? Its second application is calculation of degree of dissociation for a weak electrolyte. Calculation of degree of dissociation for a weak electrolyte. This is one more application part of Kohl-Ross law. My dear students, understand. Degree of dissociation. I'm directly going to give you the result. I'm not going to derive it, right? I'll give you the result and we'll try to apply it in the questions. Okay? Directly I'm giving you the result. Degree of dissociation of a weak electrolyte as per Kohl-Ross law is equal to molar conductivity of a weak electrolyte at a given concentration divided by molar conductivity of the same weak electrolyte at infinite dilution. What is the given concentration? What is infinite dilution? See, you know it already. I'm directly giving you the result. I'm not deriving it again and again, right? See guys, for example, you have got weak electrolyte like this, CH3COH. Let's assume I've got 0.1 molar CH3COH. Perfect. When the concentration of CH3COH is 0.1 molar, let's assume its molar conductivity at that point of time. For example, to make you understand, let's say it's 1 Simon centimeter square per mole. Perfect. Now, my dear students, let's assume you already know the molar conductivity of CH3COH at infinite dilution. Let's say it's 100 centimeter square per mole. Perfect. This particular term I'll be calling as molar conductivity at a given concentration. This is something which you call as molar conductivity at infinite dilution. So molar conductivity at given concentration divided by infinite dilution. So this divided by this will give you the value of alpha for CH3COH. It will give you the value of alpha for CH3COH. Remember it directly. Remember it directly. Remember, I hope you got to know what is molar conductivity of a weak electrolyte at a given concentration. I hope you got to know that. Now, where do we use it? That is the point. My dear students, this alpha, you can talk about its one more application. Say, for example, you have got a weak electrolyte. Let's say you have got a weak electrolyte AB. Let's say you have got a weak electrolyte AB. Perfect. If it is a weak electrolyte, it will definitely be in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. Correct, guys? Let's assume its degree of dissociation is alpha, and initially at time t is equal to 0, its concentration is C. I'm assuming that the ionization constant of this weak electrolyte is Ki. Ki represents ionization constant of the weak electrolyte. My dear students, we can calculate ionization constant of a weak electrolyte in terms of lambda m and lambda naught m. We can do that. How exactly? Dekho. This is C. This has to be 0 initially. This has to be 0. Now, at equilibrium, this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. If I want to write the expression for ionization constant of this weak electrolyte, expression will be simply C alpha square divided by 1 minus alpha. Right? It is C alpha square divided by 1 minus alpha. Now, my dear students, already alpha you know. Alpha is equal to what? Alpha is molar conductivity of the weak electrolyte at a given concentration divided by molar conductivity of the same weak electrolyte at infinite dilution. So this is C. Alpha is molar conductivity of the same weak electrolyte at a given concentration divided by at infinite dilution. What? Raised power 2. This is C alpha square divided by 1 minus alpha. Now when you solve it, you get the ionization constant of the weak electrolyte like this. C you are going to write as such. This is molar conductivity at a given concentration ka square, right? Ka square divided by it's going to be lambda naught m multiplied by lambda naught m minus lambda mc. Correct? This is how you get the ionization constant. This is how you get the ionization constant of the weak electrolyte in terms of lambda m naught and lambda mc. Perfect? Or in short, if you will be given with a weak electrolyte, just calculate its alpha first of all in terms of these two values. If you got its alpha value, if you got alpha, put it here in this expression, get the Ki value. No need to get this one as well. No need to write it. No need to remember it. Perfect? Right, guys? Is it clear? Is it clear? Is it clear? Let me know once in the chats. Let's try to do few questions on the same concept. Then only you will try to understand where it is used exactly. My dear students, I'm going to write a question. The question is like this. Just a second. The question is molar conductivity at infinite dilution of CH3COH. It is given to me as 390.7 Simon centimeter square per mole. This is the value which is given to me. At the same time, when the concentration of CH3COH is kept 0.1 molar. When the concentration, 0.01 molar this is. When the concentration of CH3COH is kept 0.01 molar, at that point of time, it's molar conductivity. So it is molar conductivity at a given concentration. It is molar conductivity at a given concentration for CH3COH. This particular value is given to me as 3.907 Simon centimeter square per mole. What am I supposed to calculate? I'm supposed to calculate degree of dissociation of CH3COH, and at the same time, I'm supposed to calculate pH of solution. These are the two things which I'm supposed to calculate. Can we give it a try? My dear students, the weak electrolyte that's given to me as CH3COH. Its molar conductivity at infinite dilution is given. its molar conductivity at 0.01 molar concentration is also given. We have to calculate alpha as well as pH. Now, what is alpha basically? Alpha is nothing. It is molar conductivity of CH3COH at a given concentration divided by molar conductivity of CH3COH at infinite dilution. This is equal to this particular term. It is given to me as 3.907 and this particular term, it is 390.7. The value comes out to be 10 raised power minus 2. So you got the alpha value. You already got the alpha value. Perfect. Now second thing. We have to calculate pH as well. Now tell me, this CH3COH, how it would have undergone dissociation. It would have undergone dissociation like this. CH3CO negative plus H positive. Correct? CH3CO negative plus H positive. Right, people? Now, initially, I'm keeping its concentration as C, which is equal to 0.01 molar. This is 0, this is 0. Now tell me at equilibrium, this is going to be C minus C alpha, this will be C alpha, this will be C alpha. So if I ask you, what about the concentration of H positive here? Concentration of H positive in the solution will be C alpha. C value already you know, that is 0.01. Alpha value you got, that is 0.01. So the value comes out to be 10 raised power. This is 10 raised power minus 2. C, alpha is 10 raised power minus 2. So this is 10 raised power minus 4. So you got the H positive concentration. If you got the H positive concentration, can't you calculate pH? pH is nothing, that's minus log of H positive concentration. So it is minus log of 10 raised power minus 4. So the pH of the final solution comes out to be 4. Isn't this clear? Isn't this clear to everyone, people? Yeah? Perfect. Perfect. Now, one last application of the Kohl-Ross law, and with that, we'll end the session, okay? Guys, is it clear till here? Let me know in the chats quickly. The last application part of the Kohl-Ross law, what is that? That is calculation of solubility and solubility product for a sparingly soluble salt. I hope you have studied ionic equilibrium, which I did a few days back only on this channel, right? First of all, sparingly soluble salt is the one whose solubility is very, very, very less. You know that, right? Sparingly soluble salt is the one whose solubility is very, very, very less. So basically, whenever I talk about the sparingly soluble salt, it means the salt with very less solubility. The salt with very less solubility. So imagine that you have got a solution in which you have got sparingly soluble salt. That sparingly soluble salt is very less soluble. What does that mean? That means the concentration of the salt in the solution will be very, very, very less. Right? If you have got a sparingly soluble salt in the container, for example, in the solution, for example, that means the solubility of the sparingly soluble salt is very less. Correct? What does that mean? That means the concentration of the salt in the solution will be very less. Concentration of salt in the solution is very less means concentration of the salt is approaching towards zero. You have got a sparingly soluble salt. My dear students, sparingly soluble salt, its solubility is very less, right? So its concentration in the solution will be very, very, very less. So I would say concentration of the sparingly soluble salt in the solution will be approaching towards zero. Perfect. Right? Now, molar conductivity of the sparingly soluble salt, I'm representing with lambda m. I'm representing with lambda m. Do you remember when the concentration is zero? When the concentration exactly is zero? At infinite dilution. Concentration is zero at infinite dilution, if you remember. At infinite dilution, root C is zero. That means C is zero. So concentration is equal to 0 represents infinite dilution. Concentration is equal to 0 represents what? Infinite dilution. So can I say molar conductivity of a sparingly soluble salt will be taken equal to the molar conductivity of it at infinite dilution? Both the things will be taken same. Did you get this particular point? Did you get this particular point? So, I believe this particular point is clear to everyone. Let me know in the chats if this particular point is clear. This is important, guys. Sparingly soluble salt, its solubility is very, very, very less. Its concentration in the solution will be approaching towards 0. So I'll say molar conductivity of a sparingly soluble salt is same as that of its molar conductivity at infinite dilution. Right? Because at infinite dilution, C value is 0. Now, let me tell you, there is one very important result. I'm not deriving it, I'm just giving you the result. We'll show its application. Molar conductivity at infinite dilution of a sparingly soluble salt. It is always equal to conductivity multiplied by 1000 divided by solubility of the sparingly soluble salt. This is one result. This is one result which you have to remember. This is one result which you have to remember. And its units are simply going to be Siemens centimeter square per mole. Whenever you will have a sparingly soluble salt, its molar conductivity at infinite dilution is always equal to kappa multiplied by 1000 divided by solubility of the sparingly soluble. I'll show you its application. We'll get to know how it exactly works. Where do we use all this? But before that, my dear students, do you remember your KSP solubility product? How do you get the solubility product? Imagine that you have got the electrolyte in this format, AXBY. Imagine how it will undergo dissociation first of all. This Y is going to be Y positive here. This X is going to be X negative here. Now we have got how many A's here? X. So this is X, A plus Y, B minus X. Imagine its solubility is S. So its concentration of A plus Y will be X times S. This will be Y times S. Something which we have discussed in ionic equilibrium, if you remember. If I want to write the expression for KSP, I'll start with the product. It's going to be concentration of A plus Y raised by stoichiometric coefficient. Concentration of B minus X raised by stoichiometric coefficient. So KSP expression has to be equal. Concentration of A plus Y, that's X times S raised by X. This is Y times S raised by Y. You can write the expression like this. KSP is equal. This is X raised by X multiplied by Y raised by Y. This is S raised by X plus S raised by X plus Y. So this is how you get the KSP expression, correct? This is how you get the KSP expression. Perfect. Now, my dear students, try to understand one simple thing. First of all, if you will be given with a sparingly soluble salt, let's say you are given with a sparingly soluble salt. You are given with its molar conductivity at infinite dilution. You are given with its conductivity as well. So easily you can calculate solubility, right? Once you get the solubility, you can easily write the expression for KSP, right? So whenever you are supposed to calculate KSP, so first of all, you have to calculate the solubility. Solubility you are going to calculate from the expression which I gave you, right? From that expression, you will calculate solubility, put it here in this expression, get the KSP of the sparingly soluble salt. For example, I'll be giving you certain questions. Let me see if you can solve those questions or not. 1-2 questions will do, and we are done with the chapter. And then we are done with the chapter. Okay. The first question which I'm writing on the screen, and I would want you guys to solve it. The question is like this. The question is the specific conductance of a saturated solution of AgCl is equal to, it is given to me as 2.28 into 10 raised power minus 6, right? Minus 6. Perfect. The question is find the KSP. Find the KSP of AgCl. Find the KSP of AgCl if lambda naught m of AgCl is equal to 138.3 Simon centimeter square per mole. Look at the question carefully and let me know if you can solve this question or not. What do you think? What do you think, guys? Quickly. What do you think? KSP we have to calculate. KSP we have to calculate. I'll just show you the procedure of solving this question. Well, my dear students, conductivity kappa value, it is given to us. Conductivity of AgCl is given to us. How much is that? I'm just writing the value 2.28 into 10 raised power minus 6, right? At the same time, molar conductivity of at infinite dilution for this saturated solution of AgCl, this is 138.3 Simon centimeter square per mole. What am I supposed to calculate? KSP. I told you in order to get the KSP, we have to get the S value. How do we get the S? 2 minutes back only I gave you a relation, molar conductivity at infinite dilution of this AgCl. Can I write it as kappa multiplied by 1000 divided by solubility? Perfect. This value is given to me, this value is given to me. So from here, you can easily calculate solubility. You can easily calculate solubility of AgCl. Now, my dear students, tell me just one thing. Tell me just one thing. This AgCl, how it would have undergone dissociation? Ag positive plus Cl negative. If its solubility is S, this will be S, this will be S, correct? Can you write the KSP expression here? KSP is going to be concentration of Ag positive raised power 1, concentration of Cl negative raised power 1. So that's going to be S ka square at the end. S value, you will calculate from here and put the value of S here, and S ka square will give you the value of KSP. Done, understood? This is the approach of solving the equation. Then calculation part, I'm sure you can do on your own. Right? I'm sure you can do that. Clear, guys? One more question I'm writing. Let me see if you can solve this or not. The question is like this. Conductivity of AgBr. Conductivity is of AgBr. It's given to me as 8.5 into 10 raised power minus 7. Right? It is given to me as 8.5 into 10 raised power minus 7. Can you tell me the unit of conductivity first of all? Kappa, 1 by R into L by A. 1 by R is conductance. So Simon. This is Simon centimeter inverse, right? Perfect. So conductivity of AgBr is given. At the same time, some other parameters are also given. Molar conductivity at infinite dilution of Ag positive. That's also given to me. How much? That is 62. Similarly, molar conductivity at infinite dilution of Br negative. That's given to me as 78. And units already you know. This is Simon centimeter square per mole. And this will be Simon centimeter square per mole too. What are we supposed to calculate? We are supposed to calculate solubility and solubility product. Calculate solubility and solubility product of what? Of AgBr. Of AgBr. Can you give it a try? Can you give it a try? Can you give it a try quickly? Everyone. My dear students, it's a very simple question. First of all, you have to calculate solubility, right? You have to calculate solubility. So solubility, to calculate solubility, you can write molar conductivity at infinite dilution of AgBr, right? How much that is as per the formula? It's going to be kappa multiplied by 1000 divided by solubility, correct? This is the expression which you have to use somehow. But as per the question, lambda naught m of AgBr is not given to me. Molar conductivity at infinite dilution for AgBr, this is not given to me. But I can use Kohl-Ross law. I can say molar conductivity at infinite dilution of AgBr. It is basically molar conductivity at infinite dilution of Ag positive plus molar conductivity at infinite dilution of Br negative. Perfect. I would say molar conductivity at infinite dilution for AgBr, it has to be equal. This particular value is given 62. This is 78. So how much the value comes out to be? 62 plus 78. That comes out to be 140, right? Simon, centimeter square per mole. So you got the molar conductivity at infinite dilution of what? Of AgBr. So this particular term you got. Conductivity of AgBr is given. So from this particular expression, you can easily calculate solubility. You can calculate solubility, right? Perfect. Once you get the solubility of AgBr, you are done with one part of the question. The second part says calculate Ksp. How do you write the Ksp expression for AgBr? So first of all, if I talk about AgBr, it would have got converted into Ag positive plus Br negative. If it is solubility is S, this is also going to be S, this is also going to be S. So Ksp expression is simply going to be what? It's going to be S square. S you would have calculated from here, put the value of S here and get the Ksp. Right? Clear? Perfect. So you can solve this question in this particular approach. Perfect. So my dear students, with this, our one more chapter is done and dusted, that is electrochemistry, right? And the next chapter, do let me know in the comment section. I want you guys to let me know in the comment section, which chapter do you want the next, right? That you are going to tell me in the comment section. I hope your complete electrochemistry chapter is completely clear. Now, please and please do watch this particular session again, right? Because all the terminologies which we discussed at the end, you might get confused afterwards, right? So do this particular session again, once again at 1.5x speed, you can watch it so that all the important things, all the concepts would be in your mind all the time. Okay? And now you can solve whatever module you have, whatever study material, whatever book you are solving, right? I'm guaranteeing you, if you would have followed these 4 sessions of electrochemistry, I believe you can solve any coaching material, whatever you have, because I've not skipped a single point here. Okay? Perfect. Chalo. With this, I'll be taking leave. I'll see you guys in the next session. Do let me know in the comment section which chapter you want the next. Perfect. Chalo. Take care, guys. God bless you all and love you all. See you in the next session. Bye-bye.